Hello, everyone. Good morning and good afternoon, good evening, wherever you are. And really nice to have you for the Emerging Open Storage Systems and Solutions workshop. I appreciate that not all of you are here live, but I'm hopeful that you'll get access to this recording. We are going to talk about emerging cutting-edge storage systems and solutions and associated software infrastructures that has been in development over the last 1 year or so. So really exciting work that will be presented here today from some of our speakers from CEA and ETOS and WECA and Seagate. We also have material that will be presented by Los Alamos National Labs, but unfortunately, the speaker was not able to be here today because of something very urgent. However, he was kind enough to agree to present the materials just after the event today. So I'll make sure that it's available to everyone. So just by way of introduction, my name is Sai Narsimurthy, and I help to run collaborative R&D from Seagate, and a few of my colleagues are also there here today. Let me just go to the next slide. So as you see, so because of the person from LANL not being available with us today, so we've sort of adjusted the agenda. So which means that the speakers that are here will get a bit more time to present their work. So we are at, if you, from EDT perspective, we are at 9 o'clock, about 9:15 now. So for the first 45 minutes or so, we'll talk about some of the work done by Philippe and the ETOS team on the IOC project. And then we'll have Thomas from CEA also talk about some of the work done in the IOC project from CEA. Then Seagate is going to present some work done on object stores and interfaces to the object store that's developed by Seagate in that portion. Then Shimon from WECA is going to talk about their architecture. And then finally, we are going to have a panel discussion, just a friendly chat between all of us. And we can think about what needs to be the priorities for open storage systems and solutions going forward. With this, I know that time is tight. But I don't want to take too much time, but I would like to acknowledge some of our funding bodies for the IOC project here, under the auspices of which we are holding this workshop. So I just present them here. The EuroHPC organization and the Federal Ministry of Education and Research and MSMT and the Swedish Research. So I would like to thank all of them. And just one word of introduction to IOC. IOC is a next generation storage and IO project that's looking at a novel software infrastructure and a platform for next generation cutting edge HPC applications. That's which Philippe and will present a bit of an introduction on that as well during his portion. So with that, I'm going to stop sharing my screen. Can I hand it over to the first speaker, Philippe Couy from ETOS. Yes, yeah, I can see the screen, and Philippe, you might be on mute, I think. Yeah.
Okay, should be better now.
Yes, so I will go on mute, and yeah, the floor is yours. And before 5 minutes before the time, I'll just give a reminder. So that we can try. So if it's like 5 minutes over or like 5 to 7 minutes over, that's fine. I think we have some flexibility since we started also a bit late, so we can adjust in the end. So yeah, the floor is yours, Philippe. Go ahead.
Thank you, Sai. So we will start this workshop with this talk about this ephemeral data access environment we are developing in the IOC projects. So I'm Philippe Couvet. I'm working in the Atos R&D, software R&D on HPC since 20 years. I'm in charge of the data management group where we are developing products and solutions for I/O on largest HPC supercomputers. And I'm also a work package leader in this IOC project, Sai introduced, and you can check more on this website. So I'll first start with some context describing what we are targeting. So the object of the IOC project is to work design a solution for the I/O on this modular supercomputer architecture, where we feel future machines will not be monolithic as they are today, but will be built from compute modules, heterogeneous compute modules, where you may have different technology, different generations of technologies, and different interconnects. So on this picture, you have the many core CPU, and GCU and GPU, and maybe future EPI nodes. And all these modules will be able to run applications and will manage their data in one dedicated multi-tier storage module. And this long-term storage module, let's call it like that, long-term storage modules will also be built from multiple technology, will be organized using an hierarchical storage management infrastructure or architecture. And so these modules will not be directly connected to this long-term storage module using their interconnect. They will more likely use high-speed Ethernet or a federated network to access their data. And so as you can imagine, on these kind of machines, accessing data from different compute modules will be longer, will be with higher latencies, and probably not good bandwidth compared to monolithic machines. So how can we rework the I/O architecture on such a machine to enable efficient data access? So that's the purpose of the IOC project. So for our solutions will be based upon inserting in the architecture what we call data nodes. So those data nodes will be connected on the compute modules, on the high-speed interconnect of the compute modules, to be able to enable fast access using RDMA protocols. So these data nodes will be the way compute nodes will do their I/O and will find that data. Second aspect, second concept is that we feel we should consider scheduling and managing workflows rather than individual application, because workflows usually exchange many data through I/O, through files. And so if on such architecture, your workflow is producing many data on module 1 and reusing quite quickly those data on module 2, it's interesting to keep those data on these data nodes that are close to these compute nodes, so that you can enable a very fast access to them. And the third concept is that we no longer want to store our long-term data in POSIX file systems, because POSIX file systems include many high-level, highly sophisticated features such as distributed log managers, and so are very sensitive to failures and are probably not able to scale at the level we need for this kind of machines. We rather target to store those data in object stores, and we will organize those data in what we call data sets. So organized group data will be grouped for each workflow in containers that will be then made available through the data nodes by what we call ephemeral services. The ephemeral services will be launched on data nodes to enable access to those data sets from the compute nodes where the application will be running. The IOC stack so will look like that. We have those long-term storage at the bottom of the picture, composed of many layers, as I said. relying on Motor, the Motor object store from Seagate, and the Phobos tape object store from CA. Both will be integrated and will form the long-term storage. And Thomas will be doing a detailed presentation on that just after. And this is the static part of the storage stack. On the top of the picture, we'll find the ephemeral part where we have the data nodes. Data nodes will be, as you can imagine, fast nodes equipped with a lot of RAM, a lot of memory, and also a lot of fast storage, such as NVMe Express disks. And will be the way where we will run the ephemeral services. Ephemeral services will get the data from the long-term storage through this dataset API, dataset managed by the long-term storage, and will expose those data to compute nodes on the modules that have been allocated for running the workflow. So those ephemeral services will be, for us, a way to make this solution compatible with current application, because you will find POSIX ephemeral services exposing data in datasets through the POSIX semantic. And we'll also introduce new protocols, an object protocol, native object protocol S3, and also a DAISY protocol or DAISY solution to store data with an organization that is defined by the physics of the application. So data are no longer organized by file and records, but more as physics objects, where you can define your cells and then define for each cell the attribute you want to store, temperature, pressure, and things like that. And so the library, the DAISY library, will enable the programming and storing data without having to care about the data organization in the long-term storage. So this will be the ephemeral services we will implement on the data nodes, and each ephemeral service will have its own API, and in some cases we'll use a client on the compute node to access the data by the application. So I already said a few words about these data sets and namespace concepts. So data sets are really data container of hosting objects. They could be seen as kind of private file system or private object store. They are dedicated to, they are owned by users, and they are just dedicated to store the data for one workflow, for one run. And data containers don't have any data organization. It's just a collection of objects. To organize the data and to expose the data through ephemeral services, we also introduced what we call namespaces. So the namespace is the way we want to organize the data to expose it. And so for a data set, you can build different namespaces, and you can even build namespaces with different protocol. You could expose the same data set using a POSIX semantic and also an S3 semantic for the same data set, depending on your need on your application. So a lot of flexibility here, separating the data container with the namespace to expose the data to the application. So now a few more words about these ephemeral services. So in this picture, which it is the global architecture of the solution. As I said, in the long-term storage, we will store objects, and the two products will rely on our Motor and Phobos. And the Motor server will be, or as it's a distributed solution, being that you can deploy on many nodes and serve the same storage space. We'll also deploy a Motor instance on the data node and allocate to it some resource of the data node, some space, NVMe space, so that some of the data that are pushed by application will be stored locally on data nodes when the application is running. And see, this Motor server will be exposed to higher level ephemeral services using an S3 exporter, the Cortex S3 server. We'll have also a talk about it later in the workshop. And this S3 server will then expose the data sets to the ephemeral services. We in the project we plan to work on 4 ephemeral services to access long-term storage data. So the first one is an NFS server developed by CEA, Ganesha, that will be able to get the data from the S3 interface and expose those data set as a POSIX NFS tree. And this NFS server is running on only one data node. It's not parallel. And so if you want to accelerate, if you need more POSIX bandwidth for your workflow, you can configure this as with a burst buffer solution in front of it. We call it smart burst buffer. So this smart burst buffer will be able to speed up the POSIX access from the client in the application, using its own RDMA protocol to provide much higher scalability for POSIX workload. And also we expose, as I said, the native S3 protocol to clients. So a client application that needs to access data sets using the S3 protocol will be able to do it. And the fourth protocol is this DAISY I already introduced, where we'll be running on data node the DAISY gateway that will do all the data gathering before putting it to the long-term storage through the S3 interface. So those are the 4 ephemeral services that will expose data from the long-term storage. And in addition, we also add in the picture 2 more ephemeral services that are more for temporary storage. So this one is NVMe over Fabrics remote access to a volume. So a compute node will be able to request for an ephemeral XFS file system, private file system for one node, and we'll be able to use it when the application or when the workflow is running. And when the workflow is terminated, is finished, the volume will just be destroyed. So it's well suited for workload where you need to store temporary data that you don't need to keep at the end of the workflow. And the GBF ephemeral service is the same idea, but here using a distributed file system. Today we propose BGFS, but we could implement any other parallel file system that could be configured on data nodes. And in this way, the application, the client nodes running the application will be able to store, again, temporary data that will never be pushed to the long-term storage for the duration of the workflow if needed. So these are the ephemeral services we will implement in the IOC solution. Now, just I put here an example just to highlight what we expect from these ephemeral services in terms of performance, but also in terms of stability. So this is an example where we run an NAMD application, so a chemistry simulation application. So it's a test case that is publicly available that you can just download here. So it was running on 12 compute nodes and has been run, the 2 runs at the bottom here. It has been run on a Lustre file system, small size Lustre file system with a maximum bandwidth of 2 GB per second. And the red box here at the bottom gives the time taken by this run for when the run is alone on the Lustre file system. So the run is running with full bandwidth and full IOPS available from the file system for the run. In this case, we run for 1,169 seconds. When we do the same test on the same Lustre file system, but generating at the same time a load or perturbation on the file system. In this case, we were running an external 1 GB per second load on the file system, which is 50% of the bandwidth. And we see clearly that just because we are sharing this file system resource with other application, this has a strong impact on the time taken by the application itself. Here we see the overhead here. So when running the same application, same condition, but through an ephemeral service, here it's a smart bus buffer, and we see that in both cases, we shorten the time because the smart bus buffer is closer to the compute node, and so it gives better performance, and it's faster than the file system. But also we see that even if when the file system is used by the application, we don't see any perturbation. We have the same time, same runtime. So at the end, we're able to save both cumulative time, because we have a shorter time runtime. And here we just save this time multiplied by the number of compute nodes that are used by the application. So that's really the motivation of our architecture, to decorrelate the application and the I/O resources used by the application and the workflow from the shared resources in the long-term storage at runtime, where we expect to save many time on the compute nodes. So now I will focus more on the end user interface and API. So such a system that I described, as you can guess, has a strong impact on users. It's not transparent. It can be transparent for the application themselves, because we will expose POSIX ephemeral services that are kind of standard. The application can just run on these ephemeral services as it's running on Lustre or any other file system. There's no difference at the runtime. But for the user, the difference is to prepare the data sets and the namespaces to organize the data themselves. And it's the same kind of activity as the user would have to do when it comes to a new machine, and it needs to download the data and then create the directories and organize the data so that the application is able to run. So that the first aspect, or creating data sets and namespaces, and then we have the second impact, which is to set up the ephemeral services. And here we will see that we are working on creating a workflow manager for that. So those two interfaces are highlighted here: the dataset and namespace preparation, management, organization by the user, and the workflow manager to be able to run the application and start the ephemeral services, monitor the ephemeral services, and stop the ephemeral services, optimize. So everything the user will have to do to handle the stack. So let's start with the workflow manager. So we design and co-design, I would say, with the use cases in the project, this interface, and we ended to a workflow manager that will be managed by user using commands, using a command line interface. The first concept we introduce is this notion of session. So we when the user needs to run a workflow composed of many applications that we call here steps, the user will be asked first to start what we call a session. And the reason here is to give the protection against multiple access to the same data sets in parallel. So when running a session, we will acquire an access token to the data sets that will be managed or used by the session, so that we can protect against multiple sessions in parallel. And we try to design this interface as simple as possible. And the solution we propose is this command start for a session, where the user will provide us with a description of the workflow and the ephemeral services in this workflow description file we will look at just after. And then the user will give us a session name. So the session name will be the way for us to remember in which session we are working. And so then when the user wants to just run an application, run the step, he will submit it to us through this workflow run command, giving us the session to run this step, and the name of the step we'll see just after what it means here. And then at the end, the user just needs to stop the session when it's finished, which is the trigger for us to release the access token to the namespaces, and so to push back the data that has been produced and which is temporarily stored on the data nodes, to push it back to the long-term storage. So in addition to those three commands, we will propose a few more. Some control commands for the workflow, for the sessions, this workflow status command to highlight where we are in the workflow, which ephemeral services are launched, and which steps application are launched, where they are. We also foresee a list command to just give back to the user the list of sessions, active sessions that we are managing in the workflow manager. And so this leads to an interesting feature, which is that the user can manage multiple sessions in parallel. So the user is not restricted to one session. It can just start many different sessions of the same workflow. So creating or processing different data or data sets. During the co-design also work we did with our use cases, we identified the need for an interactive access to those sessions, because the model we propose in IOC has the consequence that the data are not available from, for instance, the login node. When a user is connected on the login node, all the data sets he created in the past are simply not visible, not accessible. Because to access such a data set, you need an ephemeral service to be set up. So it's not obvious to manage data in such condition. And what we propose here is to create for the user interactive sessions that will be just allocating a few cores or even a few nodes in a dedicated compute partition, and configure those nodes to access to the ephemeral services that are configured for this session. So when a session is active, and the user will be able to have an interactive access to the data sets while the session is in progress, while the steps are being run, so that users can check the results, preliminary results of their simulation, can just run more processing on it to verify the simulation is going the right way. So we, at the end, we ended with a simple interface, we feel, and that seems to be manageable by users. So in addition to these commands, the user will have first to describe their workflow in this workflow description file. And for this, we designed this workflow with a few sections. So first one, name is for just recording and organizing statistics and so on. The main sections in this workflow description file are the services, which are the ephemeral services needed by the workflow. So in this example, you have one such service, which is an NFS export. We give it a name, and then we just give the attributes for this ephemeral service. The namespace to be exported, so dataset.mynamespace, to know how we need which data we need to export and how we need to organize the export or expose those data. The mount point on the compute nodes where we will mount this NFS export, and then the flavor is meant for the user to indicate the amount of resources that needs to be allocated on data node. So we don't want to bother the users with cores or gigabytes of RAMs or things like that. We just create this abstraction, which is a flavor defined by the system administrator. Could be small, medium, large, or things like that. It's user defined or system administrator defined, I would say. And so this is the unit to allocate resources on data nodes. And then second main section of this workflow description file are the steps, where users will declare their steps, which are at the end the application to be run for this workflow. So the steps will have a few attributes. First one is the name to be reused in the run command. Then the location, because the location is needed to know on which module the application will be running. Then the command, so it's for us just abstracted. It's if Slurm is the batch manager, we will just ask the user to put here the Slurm submission command for the step. And then the services that are needed for this step. So in this example, only one service is indicated. This is my ephemeral service 1 that I described here. So this workflow description file will be created by the users and will be used by the workflow manager to know all the information we need about the workflow when it's run. It will be used to create a session. When the session is started, we'll just check the syntax and we have everything indicated correctly in this workflow description file. And then each time a step is to be run, we will check for this step what are the ephemeral services that are required. And if they are not already started, we will start them. If they are already started, we'll just attach the compute nodes to this ephemeral service running somewhere on the machine. The syntax I just shared is really simple, and it's for a very simple workflow, just an example. But when you consider using the solution, it really quickly comes to the limitation. For instance, if I need one of such workflow description file for each run of my workflow, because I just indicated the namespace hard-coded in it, I will need to create many of such workflow description files for each run. So we implemented, or will implement shortly in our workflow manager, the support of variables. And so, for instance, the user will be able to put, instead of hard-coded data sets namespaces, we'll be able to put variables in the workflow description file, and then we will instantiate, we will identify the namespaces at runtime when the workflow session is started. So we could just give the name of the namespaces when the workflow is started, or even when you run a step. For instance, here we just update these variables when the step is run. So this workflow description file using these variables is much more flexible and will be able to handle many situations when, for instance, you create new data sets when your workflow is running, because you need to store or save more data that were not anticipated. So you can handle this situation with this syntax. Then a few more details about this syntax, just to highlight some aspects of the workflow manager, so design aspects. Here you have a prototype for the output of the status command. So status command will report to the user where we are in the session, in the active session. We will report back all the steps that have been submitted in the pending steps section, active steps section, and terminated steps. So terminated steps are steps that Slurm has submitted and jobs are now terminated, finished. Active steps are the jobs, the Slurm jobs that are currently running on the machine. And here the user will see, for instance, the exact command line submitted to Slurm. So if there are variables, they will be replaced here, and the user will be able to see what happened with the variables and make sure things are submitted correctly. And at the beginning, we have the pending steps where we highlight the jobs that have been submitted to the workflow manager but are not currently running. They are not running because, for instance, they have been submitted to Slurm, but Slurm has not scheduled the job yet. So in this case, we have a job ID, Slurm job ID. But it can also happen that the job has not even been submitted to Slurm, just for instance, because we are still creating the ephemeral service for it. So the main point here to understand is that our workflow manager is purely asynchronous. So when the user just submits us a command to run a step, we'll take the request into account, but it will not be synchronous. It will be processed and scheduled by the workflow manager to configure the ephemeral services, and then later passed to Slurm so that the compute nodes will be allocated and then configured to access the ephemeral services. So the whole thing is asynchronous, and so it's not blocking resources for setting up the solution. Then a few more aspects in the few more details in this workflow description file. We talked already about the location where we describe the module where the job must be running or will be running. And for us, it's important to manage it. The MSA architecture allows jobs to run on more than one module. You can create applications that are running both on CPU and GPU modules, for instance. And so for us, it's critical to know that, because we need this information to allocate the data nodes that are connected to all those modules. And so this is where we find information. But in IOC, we are also working on enabling an interesting feature, which is on-the-fly processing, or in-transit processing, that is called, which is the possibility to run some steps on data nodes themselves, where, for instance, you can have GPUs or even FPGA accelerators, and when you can advantageously run some of your steps. For instance, think about an application where we can analyze the checkpoints that are produced by the application when it's running. We can analyze the checkpoints and then produce, for instance, an image to check how the physics is evolving. So the checkpoints will be produced by the application, will be pushed to data nodes, and so will be located on data nodes when it's produced. So it's interesting to be able to create those images directly on data nodes, because it saves many data transfer back to a compute node to do the processing, and then back again for saving the image. So enabling in-transit processing or on-the-fly processing is one also of the main feature of IOC that we will address through this location attribute, and it will be quite simple for users to deploy some of their steps on data nodes. So of course, it must be not a big processing. It must be restricted to the computation that can be done on data nodes, of course.
Yeah, 5 more minutes, Philippe.
Yeah, thank you.
Thank you.
And then probably the last slide on this workflow description file details and features we will provide, which is to give control to users about the data location in the storage hierarchy. You have understood that data can be stored in the storage hierarchy in different locations, and it can be interesting for users to express how they want to have their data located before even the job is launched. And so we propose for that data movers that will be triggered when the step is launched, and for instance, with this trigger attribute before the step is launched, or even after the step is done. And so we'll enable the user to control data movements from and to the long-term storage and data nodes with some filtering capabilities we'll provide in this element attribute. So just to go quickly for the remaining of the time, some details about those data sets and namespaces. So you understood they will be stored in an S3 behind an S3 interface. So they will be organized as buckets, and we will have a default namespace where the objects are stored as a S3 object using a name that could be the POSIX path to be used for this default namespace. And we will also be able to store additional namespaces as additional objects in the bucket to organize differently the way the data, the files are presented. So in this example, you see that, for instance, this dir1, dir3, file1 file could be exposed using a different namespace as a different name, different path location. Can be convenient in some complex simulation to have a simple organization of the data. So we also discuss that with our use cases, and it seems interesting. Dataset and namespaces will be also managed by user using the command line tools. So we'll be able to create datasets, to create namespaces for the existing datasets. We'll be able also to push information in files or information in these datasets namespaces. And we choose the command line tools to enable leveraging standard POSIX tools, because when you have started an interactive session, you're able to use the standard tools, ls, find, and any scripting you can imagine to walk through your data and then create new entries, create new objects in your namespaces using as simple as possible interface and familiar interface for users. And I will finish my presentation just highlighting a few challenges of the approach that we probably will still have to address even at the end of the project. As you understand, this is really a new way of handling the I/O, including some resource management. We need to allocate those data nodes or resources on data nodes. And today, standard batch manager cannot do that easily. And we need also to probably think about scheduling workflow rather than isolated jobs. Because when you have allocated data nodes resources for workflow, you're blocking some resources, and probably it's interesting to think to finish the workflow and to schedule the workflow steps as fast as possible, just to minimize data nodes resource allocation time. So probably this solution will need some more effort on an enhanced batch and resource manager. And another challenge that we also have identified is the sizing of such a solution, because clearly data nodes are additional resources that have a cost, that consume energy. And our assumption is that those data nodes will save many compute node time. But how can we find the right balance? Compute nodes, data nodes, backend storage. Data nodes can also probably enable lower end backend storage for the solution, but it's really new dimensioning rules to be invented to size such a new solution. And I will finish here.
Yeah, thank you. Yeah, thank you very much, Philippe. It's very interesting that you mentioned the dimensioning rules. I mean, I know that we work in the same project, but just for the benefit of our other listeners, I mean, can telemetry be leveraged to do this kind of dimensioning rules? Because I think we have some aspect of telemetry in the project as well, where we can dynamically gather the statistics of the usage of resources and make some smart decisions. Is that something that you think might be like feasible?
Yeah, I'm convinced that this is the key for this challenge, to be able to measure and to model and to understand the cost of the current I/O stack. In my performance example, I highlighted how the standard application can have a very different runtime when it's run against an empty file system or a lone file system, and when it's run in parallel with productions. And so this has cost, and we need to have data to model that and to put figures and to then decide how to balance the design of the entire solution. Today, most of the time, the customer, they want as much compute node as possible. And then the rest of the infrastructure is just a cost and something that should be minimized. And the point here is that probably it's not that simple, and we should consider the entire solution in terms of design.
Yeah.
And telemetry is key, you're right.
Yeah. Thanks, Philippe. So I'll just open it up for anyone that may have a question about this from the audience. Or else we'll come back to some of this in the panel discussion as well. So any questions from the audience? Yeah, please go ahead.
You mentioned that currently the data node resources are not scheduled together with the job, right? So how does it work for now? Is it just starting a service synchronously?
Yeah, the key here, as you understand, is to separate the allocation of data nodes resources and preparation of ephemeral services from allocation of compute nodes. And we do it in the project, in the IOC project, leveraging the burst buffer plugin from Slurm. So we are able to do it today, but this burst buffer plugin from Slurm doesn't include the data node allocation capability. Slurm is just able to tell us, okay, this job needs some burst buffer resources. This is the description, please manage it on your side. But it's not Slurm that allocates the cores and the resources on compute nodes, on data nodes, sorry. So we're able to do something, but it's not the best solution for me because Slurm is not aware at all of the data node resources. It doesn't know when those resources have been allocated for a workflow. And so we should hire the priority of the same job, the same workflow, because they will be using those resources. This is what I meant at the end.
Thank you.
Thanks, Philippe. Yeah. Any other questions? If not, just a quick one. Again, I think it might be useful for our other listeners as well. I mean, which are the types of applications that might be most suitable for this IOC stack, for the ephemeral services environment? Obviously, it's very suitable for data-intensive applications that are doing heavy IO, and you can actually stage them. So any thoughts on the types of applications that might be more suited, and also maybe some one or two examples of what you have used in the project might be useful.
Yeah, so this is really interesting question. So of course, as you said, it's targeted for applications that match and produce many data, huge data. That's also very interesting for workflows that exchange many data, and where in many cases, not all, but those workflows are just writing data in files, and then the next step will be read back those data. And this architecture enables to leave those data on data nodes when the workflow is active, and so save many data transfers. And this is where this architecture is also very interesting. Yeah, and the use case we have in the IOC project are a good example of that. We have one use case, the chromodynamics simulation of particles, and it produces a huge amount of data, many steps that communicates through files, and so very interesting to leverage that. Yeah. Another very interesting use case is the weather forecasting, ECMWF, where they are running their main simulation, and that produces a huge amount of data. As you can imagine, it's run every 6 hours every day. So and those data must be post-processed as soon as possible, because the time taken to produce results makes that the data are aging, and so they are not as relevant. So they must process that as fast as possible, and this architecture enables to do everything in parallel much faster than with a standard file system.
Got it. Thank you. And I think Sean, you have a question, please go ahead.
Yeah, thank you very much for the talk. On an earlier diagram, you showed the placement of data nodes within a heterogeneous architecture. And I think that's a very good solution. I've tried to keep going back. Keep going. This one. Yep. And you're right in that if you're using two adjacent modules, so in this case, for instance, if you're using module 1 and module 2, and they share the data nodes, not moving the data is sensible. But if, for instance, you're using module 1 and module 4, how do you develop a topology that can share the data across a generalized use case where you don't actually know what's going to be adjacent?
Yeah, that's also a very good point. That's maybe can be seen as a limitation of the solution, but nothing prevents to connect your data nodes to all modules. Yeah. So this is really an example. The idea is that data nodes must be connected to modules where workflow are running and communicating through files.
Okay.
And of course, you may have situations where your workflow is not like that, and you need to use this module 4 where we don't have any data node. So in this case, we will have to go back to the long-term storage module, and of course the performance will be lower, but the stack will allow you to access your data. So it's not a limitation. You can run. Performance will not be optimum, but you can run anyway. And then it's a matter of designing the machine that fits your workflow needs. And it's easy for instance, customers running weather forecasting because they are in the same application every day. For open compute centers where people submit their jobs and you don't know, it may be a bit more challenging. Yeah, I agree.
Thank you.
Thank you. Thank you, Philippe. So I think we'll reserve some of the questions towards the end. We can thank you so much for the very interesting talk. So we'll just we'll sort of continue the same theme actually. So I'll hand over to the next speaker from CEA, Thomas Libovici. So would you like to start your talk then, Thomas?
Sure. Just figure it out how to share. Can you see it?
Yes.
Good.
Go for it.
Okay. Good morning or good afternoon, everyone, depending on where you are on the planet. So my name is Thomas Lebovici. I lead the HPC storage group at CA, and I've been working in the domain of storage in HPC for nearly 20 years now. So in these 20 years, I've mainly contributed to open source storage solutions for storage, including NFS Ganesha, NFS server running in New Zealand, Robinhood Policy Engine, Phobos, and in the framework of IOC, I lead the work package that implements hierarchical storage. In this presentation, we will focus on this implementation of hierarchical storage that have been already introduced by Philippe Couvet just before. So it's kind of funny because the last slide of Philippe was named challenges, and this one is starting with the challenges. So it's kind of continuity. So what are the challenges that comes to us for the exascale computing? First, of course, there's the increase of the data flow because the more powerful are the supercomputers, the more data they need to ingest and the more data they produce too. So what we see is that in the next couple of years, the largest supercomputers will commonly handle petabytes of data per day. But in addition to this, this data is accumulating over the time, which means the storage systems must be able to scale a lot to handle likely exabytes of data for the long-term storage. And on top of this, there are new I/O workloads that appear on HPC clusters. It's not only usual parallel computations. It's now machine learning and AI that produce many small I/Os on the system that challenges the scalability and the performance of the existing storage system. So first, let's take a look at what are the needs in terms of applications. So usually an application starts with an initial set of data. It has different steps, as we have seen in the previous presentation. And in this, it may have temporary data that are only used for one step or a couple of steps. There are data that must be kept for all the time of the computation. And there is result data, for example, that must be kept forever. to be able to be reused later or to be compared with other computations. So what we see in terms of application needs is that the exascale storage system must be able to handle different lifetimes, and it must allow optimization for each kind of lifetime. Also, the size of the different sets of data of these different lifetimes can also be very different. There can be data sets of few kilobytes, but there also may have data sets of several petabytes. In this case, so they come with different challenges. Small data sets will be very stressful for the system. They will require handling a lot of metadata, and very large data sets comes with other challenges where you will need to fit where the whole data set may not fit on the hardware, on the fast storage hardware. So you have to managing like a rolling belt where you load the data when it's used, and you unload the data which is no longer needed on the fast storage tier. Of course, there can be different access modes depending on the data. Some data can be only read, some written once and read many times, or some can be kind of pipes to pass data from one job to another. So they can be both read and written simultaneously. And there's also different access patterns in terms of random access or sequential, and the solution may not be the same. The hardware, the best hardware may not be the same depending on the access pattern. Another heterogeneity we have in the requirements is that data may be accessed concurrently, or maybe in terms of write or read operations. So for all of these different storage access patterns, HSM looks like a good solution to design a storage system that are suitable for all these different kinds of accesses. So first, it allows designing storage systems that are cost effective, because you will expend most of the money for the efficient hardware, but you also need to keep some money for the capacity part. So HSM allows you to combine the different storage technologies to have both efficient performance storage and high capacity storage. So you can, for example, use tapes or archive disks for the data which is no longer needed. In this case, the cost will be lower, and so the power consumption and the carbon footprint. It also makes it possible to use more stable devices, more robust devices for long-term storage. So it will also be, again, in terms of data safety and long-term storage. So this is the big picture of what we are currently implementing in IOC to implement such a storage architecture. So the goal here is to have a transparent migration between many storage tiers. Not only most of the storage software on the market only manage 2 levels of storage in general, one front-end storage and one back-end storage. what we try to do here is to have something which is integrated and managed in a single system, all these different technologies, starting from NVMe, using SSDs, using fast HDDs, archive HDDs, and tapes. So we want this to be transparent because it must not be difficult to use. And as part of the IOC project, we're also working on how to smartly place the data in the system, depending on the need of the applications. So when to do the movements, so on. And so in terms of architecture, we leverage several open source software. So for the high performance storage, we use Cortex Motor, which is a distributed storage system designed for exascale applications. And this software is already capable of managing several hierarchy of storage systems, of storage hardware. Not just 2 levels, but already it can manage NVMe, SSD, HDD, several kind of HDDs. But it misses the support of tape storage. So we use Phobos, another open source, which is capable of controlling SCSI tape libraries. And what we do is to do the glue to have an integrated hierarchical storage management between Motor and Phobos. To smartly manage the data allocation of data across those storage tiers, we use the Robinhood Policy Engine open source software. And I give you some more details in the next slides about how this can be used to do this. To provide access to this storage, we implement a native API that can be accessed directly to store data and to move data in the AOC HSM implementation. But we are also developing a S3 server that will be used to provide access to this data with authentication and all the features of a high-level protocol like S3. And this will be the topic of the next presentation. We're also thinking about how to move from an existing pile file system to this new system. So this is integrated to our work to make this transition as easy as possible and as fast as possible. So a focus on the different software components. Motor, which is used as the distributed storage system for fast storage. It's a storage framework. Actually, it implements many different components that are very useful for developing parallel storage, and it has tools made with very clever design in terms of transaction management, for example, in terms of telemetry. And it provides a set of features to store data, to store also metadata. It provides also a key value store function, for example. So this is really a scalable and high performance system designed for the exascale with all needed features like fault tolerance, RAID, monitoring. It has a plugin philosophy where you can develop new features and add it as a plugin. So if you're interested here, you have the URL to this storage system. A focus on Phobos. So Phobos is in comparison to Motor, Focus is focused on rather on streamed IOs. So it's rather used for long-term storage, archive storage. It's a flexible storage framework where you can use or implement specific IO adapters to store on multiple storage technologies. And in particular, it has one IO adapter for which is LTFS that allows storing efficiently data on tapes and conveniently. So LTFS is a file system on tape. It's an open source developed by IBM that gives the view of data on tapes as a file system. It also has other storage backends like Rados if you want to use it for this storage, for example. It can also use other object storage as backend. So Phobos implements Soft-Ovist layouts to organize the data on the different storage technologies. So you can mirror the devices, you can do some read or erasure coding on the devices, and in particular with tapes, it allows implementing read on tapes. So you may have, for example, 2 tapes of data and 1 tape of parity, and when a tape is unfortunately broken or lost, you can rebuild the content of this tape from the 2 remaining ones. So of course, to access tape, Phobos implements the scheduling of tape mounting by sending SCSI commands to tape libraries to mount the tapes, and it tries to minimize the mount operations to optimize the whole bandwidth of the system. And as access points, it provides an API and a S3 server. So if you're interested in this project, you can also find it on GitHub in the Phobos storage project. Now focused on Robinhood policy engine. So Robinhood, the main thing is that it collects there are tools to collect information from the system you want to manage. So for example, if it's a purely POSIX file system, you can scan it regularly. Yeah, and you can also, for systems that support this, you can also register to events from the file system. So Robinhood can be aware in near real time of what happens in the file system. And with this information, it fills a database. So in this case of scanning, this database is refreshed when you scan. In the case of file system, the storage system provide events. It updates the database near real time. So to give an example of file system that provide events, there is, for example, Luster that provides a changelog mechanism. Motor provide a similar system with its FDMI interface. You can also use it with POSIX by using FA Notify, the FA Notify feature that allows to register to what happens in the file system. So with the content of this database, you can easily query for attributes of files. So for example, you can request to give me all the items that are on a specific tier and that are older than a given time frame. You can, yes. And depending on what you put in this database, you can also save the extended attributes, and then you can trigger policy based on these extended attributes. So the main point here is that the database is much easier to query than the file system. And it's optimized for multi-criteria researches. So this software is also available on GitHub in the Robin Hood Suite directory. So coming back to the IOC HSM implementation, we take these different open source software and we add new features for the data management. So a first concept of the IOC storage is Philip told a little about that, is that the data is organized as objects and data sets. So an object, it's primarily a base information. It's a unit of, it's a data item. For example, it can be a picture of one cat. And these objects are grouped into data sets, which allows the application to easily handle a group of objects. So for example, a data set could be pictures of white cats. So it's a family of objects that we want to handle together. So for example, the application can request to load all objects from a data set to the fastest storage level. Another innovative feature we implement in IOC is the concept of ints and the way ints are used by to optimize the IO in the system. So ints is a way for the user or the application or through the workflow to give information about the intent in terms of using the data in the near future or on the long term. And ints can be specified at any point in the life of a file. When you create a file, you can indicate how long you plan to write to this file, or you can indicate an access frequency, but you can also specify this later if you change your plans or if you made it more precise during the computation. And ints in this system, ints are specified just by a simple set attr call. So just as simply as you change the owner of a file, you can set an int. So here on the right, you have a list of a list of what ints we find interesting to set in the system. So the first one, which is very similar to what exists in POSIX with POSIX fadvise, it's an intent of access on the short term. So for example, the application can indicate it will continue accessing the file, or in opposite, it can indicate when it's done with a file, it no longer plans to read it again or nor write it again. So it can indicate it won't access it. And then the HSM, being aware of that, it knows that it can move the data out of the flash storage, for example, to make room for running computations. It can also indicate it will no longer write to a file, even if it still accesses it. So in this case, we can archive the file, but keep a copy on the fast storage. And there are other things that are interesting to know for the HSM management, which is the estimate lifetime, if the file will be deleted in a near future, the access frequency. We can also imagine having predefined policy at the administrator level. For example, having a policy temporary data, a policy for intensive IO access, and a policy for keep forever data. And in this case, the user can simply specify a hint like temporary data or archive data. So all these hints can be used by the system to optimize the data placement. And there are two more things that are maybe interesting and that even simplify all this process. In case the application or the user don't specify anything, we can use machine learning and AI to predict the lifetime. We'll see that in a couple of slides. And also categorizing the object can be useful to determine the best data placement policy. So once the user has specified the hints on his object or data set, here is how it can be taken into account. So hints, as I said, is kind of set by a set-attr call. So they can be attached to objects as extended attributes. And then the policy engine that is as registered to the events from the file system is aware that the user has set a hint for the data. And then it can make a movement decision based on this hints. So depending on the policy, after some time, the policy engine will be able to schedule the data movements to move the object to the right location when it's needed. So for example, the policy engine can run a policy which would be if the expected lifetime is now expired and the object has not been accessed within the last hour, and that, or perhaps if the application has set won't access hints on it, then move the data to slower storage. So you see that the movement policy can be user-driven thanks to hints. We can also integrate the interpretation of hints directly in the IO API, for example, to trigger synchronous movements of data. So we could imagine having a set-attr call which would be synchronous and would give back, would return once it has moved the data. So a few words about predicting file lifetime. What we can see on the HPC systems is that a user or a set of users often use the same set of codes. These codes generate the same name for the files, and when looking at the output of a compute code, you can then predict what will be the future usage of each file. So for example, if you see a file which is called something.log, you can predict that this will be written sequentially. There will be often written and never read, and sometimes for debugging purpose, it will be read by the developer of the application. So looking at the user, the code, the file name, gives very good results in terms of file lifetime prediction. So I listed here two publications on the subject that gives very good results. So this then it avoids the administrator to have a look at every application running on the cluster to set specific policies for each of the codes. This can be learned automatically. So of course, the first few times a new application runs on the system, you cannot predict that, but on the midterm, after a few runs, this can be learned by the system. Another smart thing we try to do for the data placement is to use machine learning algorithm to classify objects per similarity. And the goal here is to group similar objects together to optimize the storage usage. Because if you group similar objects together, this will boost the compression ratio on this device, and the deduplication mechanisms will find much more pieces of data to be deduplicated. So it's an interesting approach to group these to group the objects based on their similarity. So again, I listed here some of the publication we've made on the subject. People from the Addressee project made on the subject. A few words about the HSM implementation in Motor. Yeah, Motor allows to store objects as multiple pieces of data that are managed independently in terms of hierarchical storage. So, for example, on this picture, this is the view of a single object, which is actually split into different regions. So there could be pieces of data located on tier 1 to 3. Some other regions of the files could be only on tier 3 and 4. And this way, if you need to manage very large objects, you can easily only load the active part of this data set in the fast storage tier. So this is very convenient and very flexible way of managing very large data sets. And for example, you can if you have many objects and you want to run to read the header of each of them, this way you will only load the fast tier with the header of the files and not the whole files. So some more concrete stuff here with an example of run of using the HSM. So it's so in this application there is an already existing set of data which is green. No, which is actually the green part here at the beginning. So initially all the existing data is in the archives, so the archive is green. Then when the application starts, so at the beginning it will request to stage all this data in the archive to a fast tier, which is represented here in orange. So here you see all the data from the archive being staged to the NVMe devices. So at this point, the data is replicated in the two tiers. Then in the second phase, there is the application running, and that happens the objects that were pre-existing. So at the end of the run here, we see there is much more data in the NVMe than on the archive, because there is the initial set of data which has been appended by the new data returned by the application. And then, as a first phase, we see that once the application has run, the data is progressively flushed to the archive. So we see here the amount of data in the archive, which is increased. And at the end, there is remaining data which is cached in the NVMe level, which may correspond to data which has been the more recently accessed. and then we run a command to clean it all, because the application no longer need the data after that. So only the data in the archive remains. So this gives an example of what the IOC HSM implementation can do. So to conclude, the IOC HSM, we try to develop hierarchical storage management with many tiers of storage, starting from the fattest NVMe to the most capacitive, which is tapes. So this is really different to what exists today on the market, where systems only mostly manage 1 or 2 storage tiers. So we have bring new features in terms of data management with, for example, INS, and also by taking advantage of machine learning to help with the data placement, to avoid the administrator to write very specific policies for each of the compute code running. So everything of this is based on open source solution that will likely be improved during the implementation of IOC. So it's open source, so your feedbacks are welcome if you want to test them, and it's always open to contributions. Thank you for your attention. Do you have questions?
Yeah. Thank you, Thomas. Thank you very much. It's very good to see how the story continues from Philippe's talk to yours. So just a quick question, just for our audience. So I know that you have open source work, like you have the work on Robinhood and Phobos. Will the work that's going to come out of IOC on the HSM, will it? I hope that will also be available to the community.
Yes. So in the framework of IOC, we will improve the different software that I presented. So this will be available to the community. And as for the glue, yes, I guess the API that will allow managing it as a consistent and aggregated system will be available, yes.
Okay, yeah. Thank you.
So it's part of the, it must be already available as part of the IOC. There must be an IOC repository on GitHub.
Got it, okay. Thanks. So let's see. Sean, please go ahead.
Thanks, Sai. Thanks, Thomas. Can you go back to slide 20? I think it's slide 20.
Yes.
Yeah. So if I understand this use case right, essentially the application doesn't run until all the data has been fetched from the archive tier.
Yes, in this particular test, yes.
Okay, but in principle, you could start essentially doing your application run at tier 0, but have the IO scheduler say, okay, I'm going to need to bring in bits. So you start off reading from the archive tier, and then you start pre-caching into the fast tier ahead of when you're actually going to need it. So your application will gradually speed up as more and more data is moved out of the archive tier into the fast tier. Is that possible?
Usually it depends, but I mean, if the data is on tape, it may be quite long to stage to read it back to the fast storage. So if you allocate
but if
thousands,
it was disk storage, rather if I consider tier 3 disk rather than tape. I agree, tape is a different case.
Yes, exactly. So yes, that's the big thing. If the data is on disks, the application can start immediately and it can read data immediately, even if it's slow. And indeed, it becomes faster and faster as the application runs. If the archive is tape, it's better to get back all the data before you start running, because if the application has allocated thousands of compute nodes, these thousands of nodes will be idle for a long time before being able to compute.
Yep,
So it's a waste of compute power. So if it's possible to wait, it's better to have all the data on the fast storage before starting the run, and so the compute power is used the most optimal way.
Yep. And maybe your application has to adapt to be data aware, so it knows when the data is staged appropriately for you. Because then you could have multiple streams coming off of tape, and then you just fire off as the data becomes available.
And
okay.
I think in the workflow system presented by Philippe Couvet, it stages the data before the run to use compute power the most optimal way.
Right. This is what I just wanted to say. The workflow manager will take care of that, and will take care of not allocating compute nodes before the data are staged in the right location.
Perfect.
But from my experience of running an HPC compute center, I think there are two cases. If the user use an interactive tool for the processing, so if it's for visualization, it prefers start immediately and at least have something to look at, even if it's slow, rather than waiting 1 hour for its data to be ready and to do his visualization.
Yeah. Yeah, so very true.
So it's the interactive versus batch need.
Yeah. Thanks, Thomas. Also, just one final question is on the policy engine, right? So I guess you'll need some smarts, maybe some sort of AI, very basic, rudimentary, to understand, to take some intelligent decisions on the staging. Is that is there a plan to work more on the policy engine, or do you think what you have is sufficient for the purposes of the project? Of course, you can give explicit hints, but if the policy engine can learn from the workloads, so perhaps you don't require a very deep AI engine per se, but some sort of rudimentary intelligence, right? Any thoughts on that?
So the goal here is to make some okay, let's say the technical work in the policy engine to be able to feed it with AI-based prediction. So the idea is that the prediction mechanisms, for example, the file lifetime prediction mechanism can attach information to the objects that can be then used by the policy engine to schedule its operations. So, for example, we can attach to an object the predicted access duration, and then we can configure in the policies move the files whose the predicted duration is expired. So this is how we plan to link these two components.
Got it. Okay. Yeah. Thanks, Thomas. Any further questions from anyone? So if not, thank you, Thomas. We'll come back
for your attention,
and we'll have some more discussion during in the end. So I think now what we'll do is we'll take I see that one of the speakers joined us as well. Hello, Shimon. So what we'll do now is that we'll take a 15-minute break. And I think there's also a comment from Sean as well.
Yeah, don't worry. I just like the idea of using extended attributes for that. I think that's quite a smart move.
Got it. Yeah. Thank you. So we'll come back in the next 13 minutes, which is in my time, it is 4 o'clock. So it's going to be 11 o'clock Eastern EDT. So we'll see you in the next 13 minutes and we'll start on the hour for the next talk. So have a nice tea break, a coffee break, and see you in the next 12 minutes now. Yeah, start on the hour. Yeah, see you soon. Yeah, hello everyone. I think just on the hour. I'll just wait for a minute for everyone to get back. So I think meanwhile we can get the next speakers ready. So Andre, I think you're already online. Hope you can hear me okay.
Yes, I will try to share the.
Perfect. Yeah, go for it, Andre.
Sorry, it says I need to configure something in my system.
No worries. Yeah, take your time. It's okay.
I will relog in now. It requires to relog in.
Yeah, no problem.
Okay, I'm back. Let me try to share it again.
Yeah.
Okay. Can you see it now?
Yeah.
Good. So let's start. Sai, let's start or we wait?
Yeah, go ahead.
Okay. Hello, my name is Andriy. I'm working in Seagate in the Cortex project for more than 10 years already. And today I'm going to tell what we did not long ago, recently, with integrating Ceph S3 into Cortex. Yeah, we have two parts. I will tell about Cortex, and Zuhair will tell about the same thing he did for DAOS, which is Intel's storage system. Here is agenda. Let's go. So a few words about S3. S3 stands for Simple Storage Service, a cloud-based object store provided by Amazon. S3 protocol is used by other storage systems like Min.io, Ceph, from which we took a GW S3 server. It uses HTTP requests and RESTful protocol. It operates with objects. Object is a basic storage unit in object storage, and it implements authentication and authorization when someone tries to access the object. He needs to provide the key. The user can specify ACLs and multiple versions for the objects as well. Objects are stored in buckets, right? It's like a container for the object that where you store some set of objects for the. So mainly used for the convenience. And yes, S3 does not have a hierarchical structure like POSIX. All objects, the namespace is flat. Well, you can use slashes and you can create like hierarchy in the buckets for objects, but all these slashes will be part of the object name anyway. So because it doesn't use the hierarchy, it doesn't suffer from these problems like POSIX suffers when accessing the files. So you can very quickly access. It's O1 operation, complexity of operation to access any object is O1. It doesn't depend how deep the object is in the file system, in the hierarchical file system. Okay. So Ceph and RGW. So RGW, right, Ceph is an open source storage system that provides object, block, and file storage. It's very well known in the community. It's there for a long time, more than 50, maybe 15 years, maybe more already. And it has a Radas gateway, which implements S3 and Swift API to Radas. So not long ago, maybe couple years ago, they introduced this project they called Zipper, and they implemented this a storage abstraction layer in Radas gateway to make it easier for other object storage system to use a Radas gateway as a S3 frontend for their object storage. Which was quite handy, and we thought, why not to try to implement Motor SAL layer to use it in Motor, and this proved to be very successful approach. We managed to implement the proof of concept in about 1 month, maybe, me and Sining, only 2 developers. And we did basic operations like put, get, even some basic versioning was also working. Well, you know, I will not say too many words about Motor because it was already said before by 2 presenters before. Motor is a core part of Cortex, very similar like Radas is core part in Ceph. And Cortex is just an ecosystem around Motor, which provides many features like monitoring, deployment, etc., etc. And Cortex is open source, of course. It's Apache 2 license, and it's like a Swiss knife, which you can use to build, anyone can use to build his own storage system. It's optimized for mass capacity, data-intensive workloads, optimized for hard drives, but not only. You can use it, of course, with SSDs, etc. Yes, and we adapted RGW to provide S3 API to Motor. This slide, which tells a little bit about what is Motor internally. So you can see here we have data service for the data flow. You have disk services. You can see disks underneath, and on the top you can see Motor client library. So let me say a few words how Motor is different from, let's say, from Radas. Motor was designed, the philosophy of Motor design was from HPC world. So it was designed originally. The basic ideas put underneath it were made by the same architects who designed Lustre. Peter Bram was the original author of motor, and in HPC world, as you know, it's a little bit different from the cloud world, right? In HPC, you usually have a computation nodes, which are very powerful, and you have storage nodes, which are not so powerful. And in cloud, it's not so. In cloud, you have mainly you have thin clients and big, very big cloud clusters and servers. So Ceph, this expresses the difference how Motor and Ceph or Rados works. For example, Rados, when you send the data to Rados, the parity calculation, erasure coding calculation, it is done at the server side. While in Motor, erasure coding computations, they are done in Motor client library, which is client side. So this powerful computation node, they do this parity calculation. But as I told, Motor is like a Swiss knife. You can combine and you can put this with RGW. We put these servers in Cortex. You can put them together into the server nodes, and you can use Motor in cloud as well. So it gives you flexibility. You can put the computation intensive thing. You can separate them from server with Motor. Yeah, here are some features on the left mentioned, which were mentioned today already. I will not repeat them. So let's dive a little bit into the code, in particular into the put data path in RGW. So another interesting feature of Motor is that you can set unit size of your object depending on the size of your object. Unlike in many systems, including Rados, the unit size, which is also called cluster size in usual file system, they are fixed for the in best case they are fixed for pools. What's the problem here? Let's say you have small files like 10 kilobytes or 32 kilobytes files, but you have a huge number of them. So if you will use 1 megabyte unit size for such files, you will waste about 900k bytes on each object. So you can imagine what a waste of the space it can be on such small. From the other side, if you have object like gigabytes size, and if you use small unit size like 4K, the time to download or to upload such gigabyte object will be huge, right? But now you can ask how this is handled in normal file system, like in TFS file system. We know that in TFS has 4K cluster size and it works fine with gigabytes. Well, it's different with distributed systems. With local file system, these 4K blocks, they are aggregated and they are sent to disk in aggregated way in the big blocks. But in a distributed file system, every unit has to be sent separately to every server, right? To every disk. So you cannot aggregate them so easily. You can. So this is the thing. Motor allows you to set different unit size for each object depending on its size. So how do we, now is the question, when user tries to put object, put S3 object, how do we know what the final size of this object will be? You cannot tell it from the beginning, right? So what do we do usually? We, let's go to the next slide, yes. Let's look at the API of RGW. There are three functions: prepare, process, and complete. So when user uploads object, it calls before uploading, of course, it calls prepare. But when upload starts, it calls process callback several times for each chunks of the object. And these chunks, they usually about 4 megabytes, something like this. And then when upload is finished, when user S3 objects upload is finished, it calls complete at the end. So how do we learn? How do we learn the final object size? What we do, we don't start creating motor object until we accumulate some amount of data. There is currently the oriented size is 32 megabytes. If we make it more larger than 32 megabytes, it will RGW process can become very huge if a lot of S3 clients will start to upload objects at the same time. If we make it very small, the unit size may be not very optimal, right? So we selected based on the experiments this 32 megabyte value, and when we have up to 32 megabytes, we now can create and estimate the unit size and create motor object. And then when complete calls, we know the full object size, so we know the full picture. So essentially after 32 megabytes, we start writing motor object. Okay, and here is the flow. There are some objects, internal RGW put object. It's internal to RGW. Motor store, it's what we implemented in the SAL layer. Motor atomic writer, it's also object implemented in SAL layer based on atomic writer, which is part of SAL API interface. So you can see here, prepare several times, process is called, and complete at the end. And when complete is called, we create a record in motor KV storage with the metadata, with S3 metadata. And not only S3 metadata, we also have motor feed to save. We also have to save object size in this metadata. We do this at the end when complete calls. A few words about data layout, where we store users in user info index. These are all index. These are motor KV distributed index. In motor, it's called DIX, distributed index. So these indexes are motor KV distributed indexes. So bucket instance index stores information about all buckets for this user, and bucket index stores information about all objects in this bucket. Okay, here is the picture of how the difference of how Rados and Motor stores the object. For example, in Rados, object metadata is stored in the header part of object, while in Motor metadata is stored in bucket index, and in the data we have only the data. We don't have any metadata in the Motor data. A few words about performance issues we observed when we implemented SARL-Rail. So at first, performance of put operation was fine, but get was really terrible. For example, for 64K objects, you can see here that performance for get was only 4 megabytes per second, while in Ceph it was about 1 gigabyte per second. So it was something very terribly low. And as appeared, the problem was actually with the configuration of Ceph. The default value for worker threads is 512. And when we changed this to 10 threads, the picture became completely different. Improved more than 10 times. It became 54 megabytes per second, and time to first byte also decreased from almost 1 second to 69 milliseconds. And then we added caching also, caching for metadata, caching for user information, and it also improved about 3 times. The value for get became about 150 megabytes per second. And for first time to byte, about 25 milliseconds here. Okay, some other test results for 1 megabyte objects. As you can see here, it was interesting that for put we get even about 2 times bigger value than Ceph provide. For Ceph, it 100 megabytes per second. We got 200 megabytes per second. For get, we got 600 megabytes per second, which was much closer to the values we have for get with Ceph. Still lower, but the thing is, Ceph does very aggressive caching of on get. That's why it has very good performance numbers for get. Our caching we implemented in our S3 layer was very rudimentary. We used time-based caching, so that's why we couldn't beat it. For 10 megabyte objects, we got the number for get, which is almost the same as Ceph has, 1 gigabyte, and put was a little bit lower. No, you can see the last number for put was 574, which is almost the same as Ceph has. And 32 megabyte objects, you can see that for get, we've got even higher number here than Ceph. And for put, still we couldn't beat Ceph here for put. Anyway, it was a proof of concept. Of course, we didn't do any performance. We didn't have time to do some big performance optimization at that time. So here we are. What's 5 minutes left? Quickly on some interesting other issues, like concurrency issues. For example, imagine that several S3 clients are downloading at the same time the same S3 object, let's say for about 10 gigabyte. What do we do? How do we make sure that we don't corrupt the data? Because AWS protocol specifies that the object data should be consistent. It should be not partial at the end, and it should not be mixed, right? And the last successful write is the one that should be remained in the system. So how do we achieve this goal with Motor? In the early implementation, each new S3 object had the same Motor object feed. And of course, you can imagine that having writing the same object with the same Motor feed at the same time, it obviously violates the very first requirements here, that the data to be consistent. So how we resolve this issue? We always generate unique Motor object ID, Motor feed, for any new S3 object. So even if same S3 object is written by different S3 client or from different nodes, they will have different Motor feed underneath. So underneath in Motor, we will write different objects. Right. So, and when writing is finished, we update bucket. We add to the bucket index the information with the metadata of this S3 object. So the last successful one will remain in the system, and another one will be deleted eventually with a garbage collection. This is how we solve this problem. Multi-part. I have a few minutes left. Multi-part, just a few words. What is multi-part? It's S3 protocol allows, when the object is huge, like 10 gigabytes or even more, it's very likely that you can have interruptions, you can have disconnection and so on. So S3 allows you to upload the objects in parts, essentially dividing the object to parts, and you can upload them separately. And when some disruption happens, you can upload only that part, not the whole object. And also you can upload them, of course, you can upload these parts in parallel, which also improves the performance of upload. Implementation notes, each part is stored separate Motor object. There is another bucket, another Motor index to store information about object parts, etc. Here is a sequence diagram for multi-part. I will not stop here. Identity access management. I will only mention here that there is slight difference between what AWS provides and what Rados.
Andre, sorry, just 5 more minutes, please. Thank you.
5 minutes? Okay.
Yes, yeah.
Yeah, I'm finishing already. Here, where were we? Yes, so AWS S3, it has an S3 account, which Ceph RGW does not have. But the good news that Ceph is going to implement S3 accounts as well and be more compatible with AWS. And here is the list of IAM features, which we support currently: users, credentials, tenants, permissions to buckets, users and policy, etc., etc. This what we support. Right, and this is the final slide. Few words about what we learned from the experience with this integration with RGW. So, knowing motor client API was essential to implement proof of concept in a short time. At the time when we started doing it, it was in this last winter. SAL API was still evolving, so even during our first PR, it was changing a little bit, but the changes were not big. Looks like SAL API is in the final shape, which is good. You don't have to implement everything in the SAL API to make simple operation work, like put, get, etc., which was handy. We implemented it gradually, incrementally, I would say. We first implemented put operation, then get, and so on. It was exciting to see how the system was growing in functionality as we were implementing these callbacks in the SAL API and was testing. And it was relatively easy to implement basic versions of some advanced S3 features, like, for example, object versioning and locking and multipart. And even, as I mentioned, we implemented some basic caching, time-based caching. Fine-tuning of Ceph is required to get good performance numbers for some workloads, like like I mentioned before, for get, for example. And Ceph community appeared to be quite friendly and welcoming. So they accepted our SAL implementation into Ceph repository, and you can find it there. It's the very basic first version is there, and we are in process of updating it. Future plans is we adopted Ceph RGW in Cortex, and we stick with it, and Cortex is going to be to proceed and with RGW, and Cortex S3 developers to contribute back to Ceph with bug fixes and feature developments, etc. Yeah, that's basically it from me. Zuhair.
So I'm gonna. Could you stop sharing your screen so I can share yours? Mine.
Yes, sure. How to stop it?
Okay.
Yeah.
Okay. Right. This is okay. Hello. Hello everyone. This is Zuhair Sadler, and I've been working on the Deos project for the past, like, it's going to be almost a year. Like integrating Deos with Ceph. So let's go into a bit of the agenda for us today is going to be like background, a bit of design and performance, and then we're going to talk about future work, and then there's going to be a shared Q&A about both parts of the presentation. So Deos is an open source object store created by Intel. It's designed primarily for massively distributed non-volatile memory and storage class memory, something like Optane or NVMe, NVMe Express. In Deos, there are Deos objects. There are the basic storage unit. They're accessed by 128-bit object address. and objects are grouped into containers. Containers have like a private object address space, independent of other containers. It's similar in concept to S3 buckets. And then there is also a pool. A pool is like in Deos defines all the storage target memberships and contains like containers within it. So a bit more about pools, like you can see that, yeah, so the pool can contain like multiple like tiers of storage, like could store some data in the SCM and the other parts are in NVMe. It could only be like one part of the storage, and it like you can like add or remove nodes as necessary. The pool is divided into shards, and like each shard is in a specific target. You can expand the pool either by expanding like each shard on its own or by adding more shards and more targets. And a bit about the object API, like objects natively in Deos are accessed through a multi-level key array. So this is where we have two keys inside the object. There is like a distribution key and an attribute key. So all the attribute keys under the same distribution key are guaranteed to be on the same target or in the same shard within the pool. Yeah, and there is also a flat key value API. It's like much simpler to use and handles all the sharding for you. And then there is also an array API, which is a one-dimensional array of fixed size elements. You can basically use that to store files or like any large string of data. So Deos implements on top of the basic API, it implements a file system or a file system-like API. It's like where you can mount a Deos container as a POSIX file system using Fuse daemon called dfuse. And you don't have to use like the Fuse daemon. You can just directly access it through libdfs. So it exposes the POSIX emulation to applications. Within DFS, there are files which are like basically array objects, and there are directories like listing like multiple containing files. It supports symlinks and extended attributes. And the DFS API closely resembles the POSIX API, but it's like the difference is in performance and the internal structure, of course. So here's how directories are represented inside the DFS, the file system. It like each entry in the directory is under a single D key, distribution key, and all the attributes for that entry, including like the file name, like access time, chunk size, and all of that, are under our A keys, attribute keys under the same D key. So they're always going to be in the same target. And you can always add extended attributes as you need to. So how this ties into the rest of the presentation, we are like creating an S3 API accessing to Deos. We do that similarly. We use the Ceph RGW. We implemented the storage abstraction layer for Deos, and this allows us to access the Deos API while also allowing other applications to access via dfuse or directly. We had a like sub goal in the design that we wanted to maintain as much interoperability with POSIX as possible. So the easiest way to do that was to build the Deos style on top of libdfs directly. So this still skips all the kernel and all the Fuse stuff, but like maintains like ability to operate with dfuse. So what we do is that we like mount a pool. The Deos pool is used for a the S3 system under a single pool, and then we create. So we will look at how we're mapping. So we map each S3 object to a DFS object or a DFS file, and the S3 buckets are mapped into Deus containers. The whole system is mapped into a pool. Every attribute in S3 could be stored in extended attributes as we need to. And remember how Andre talked about slashings in object key? We translate those into DFS directories so that we maintain interoperability. So for example, if we try to write a file to test foobar file, you will see that we have like a directory structure that's created test foobar file. Okay, let's look a little bit about the code. So like Sal provides all the abstract classes and methods. For example, in like using S3 put, we went through these for motor, but as a reminder, we have a prepare operation starting the processing, and process is called every time we want to process a chunk of the data. And then the complete operation, like method is called when we are done with the processing. A bit of how it's mapped. So when we like use prepare, we create all the directories in the path. So we divide the key by slashes and create directories or use existing directories, and then open the file. While for each process operation, we issue a DFS write, and we don't have to worry about the chunking data because, yeah, sorry, can you still hear me? Yes. So the yes. So for each, the DFS already chunks the data for us, and it's processed. In the complete, we close the file and release all the resources. Similarly, for get operation, we have like a DFS lookup, which like basically traverses the directories and finds the path for us without having to open each directory. And then we issue DFS reads right away. When we're done, we release all the stuff. Delete is similar. We look up the file and issue DFS remove, which removes the file for us. Now, of course, we have to store users' data. So the S3 API stores some information about each user, including the user ID, the access keys, emails, and so on. So the user info is shared across the system. We have a special metadata container called metadata, and it allows access to users and to make it easier to access user by different things. We use symlinks. So for example, if you want to get a user by access key, we like basically follow the symlink to the user that has this access key. We also store information about pending multi-part objects. So we're going to look at this in the next slide. A bit about multi-part. Again, it has like 3 different operations, and these are all like separate post operations. So like HTTP requests, I mean. So when you create a multi-part upload, we generate the multi-part upload ID and create an upload directory in the metadata bucket that stores information about this upload. Then there is like, we have multiple operations for uploading parts. So we write them to separate objects underneath the upload directory. And then in the complete, we create the object in its like correct key where it has to be there. And then we copy the data from each uploaded part, like and ordered by the part ID, and then like clean up and delete the upload directory. Like the process is a bit more involved, but this is like an overview of how it works. We also do support versioning. So basically, when you have versioning enabled, you can have multiple versions of the same object, and each has a version ID. So we store the version ID in the object name between brackets, and we maintain a symbolic link to the latest version, so that when you want to get the latest version, you can always find it. This is still work in progress. We are currently most of our code is under the Ceph repo. We are moving most of that to a new Deus library called libds3. This is like to make testing and like maintainability easier for the Deus team. We are doing some tests. There is a so there is a repository provided by Ceph called S3 tests. We plan to expand the test suites to include other test cases like versioning and so on. And so far of these tests, we have 35% of the tests succeeded, and we're debugging the rest and to aim for full S3 compatibility. We are also doing performance testing. We want to understand the bottlenecks and resolve them, and eventually we want to add caching. During the performance testing, we're not only doing performance testing on Deus, we're also doing additional performance testing on Motor implementation. So in the future, we would like to add a way to write through DFS. So the current system allows you to only read through DFS. We would like to make existing DFS containers accessible via S3, so that you can read and write from DFS or read and write from S3 and have them compatible. We are also looking to implement a shared namespace. So here, this is a project that's going to be happening soon. We want to join Cortex and Deus under a shared S3 layer, so that we can send the metadata to the faster Deus system, because it relies on SSDs and storage class memory, while the rest of the data could be stored in Motor on HDDs, which is cheaper, but still gives good performance. And users could choose what kind of storage they would like for each bucket. So here are some links. You can look at them when the slides are shared for the design document. And thank you so much for listening. We are open for questions, Andre and I. Thank you so much.
Thanks, Zuhair and Andre. Thanks for sharing this very exciting work where multiple communities got together. It was the Deus community, the Ceph community, the Cortex community. So it was very interesting and exciting, I think. I mean, maybe Andre and Zuhair, can you tell us a bit about some of the lessons learned or any challenges, working with across communities, right? Like you're trying to maybe get answers from the Deus community, and maybe Andre, you're trying to converse with the Ceph community and stuff. What was your general experience? Was it very easy, or was it a bit hard, or were you able to do all your work on your own with minimal cross communication?
I would say that's this third variant. We were able to do the work by ourselves, mainly with Sinning, and then maybe there were a few minor questions I don't quite remember by now, but yeah, mainly we could figure out by ourselves what we need to.
Yeah, and I can also say similarly about the Deus implementation. Andre did the first proof of concept for Motor, and that was very helpful in creating the proof of concept for Deus. So basically following the same stuff.
Yeah.
And the Deus team has been collaborative. There have been some issues with things not being documented well, as with most open source projects, but we have contacts with both Ceph and Deus, and to talk through these things. So yeah, it's been pleasant so far.
And from Motor side, there was no need for us to ask anyone, because we were quite fluent with Motor already, with Motor client API. So it was easier for us from this perspective than for Zuhair. Zuhair had to ask Deos people how to how to use the interface. It was probably more challenging for him.
Yeah, I guess it I think one of the things is that the importance of good documentation in open source projects, right? So it looks like probably you could refer to very good documentation from, for example, the Ceph community, and I think Deos is probably getting there as well. Possibly. The Ceph community probably is a bit more mature in terms of how long they've lasted. Deos is a bit more newer. So I guess, Andre, you're happy with the documentation that you had from Ceph. So that's what it sounds like, right?
They didn't document explicitly this cell layer, but the source code, in the source code, it was more or less okay to get the idea what this or that callback is doing. In the case when it was not, yes, we had to dig a little bit deeper into the source code of Ceph, and we did it. I would say quite often. But in general, Ceph code is written okay, I would say. So it was quite easy to see from the code what this or that callback is doing or has to do from the source code. There was no, I cannot say there was some documentation which documented this API explicit. There is documentation, but it's quite general about overall architecture of Ceph and RGW. It's not very detailed.
Got it. Yeah, I think when we share the recording to the community, I'm sure the Ceph community and the Deos can also see what you guys are feeding back to them as well, because you're using some of their outcomes. So is there any other feedback that you want to give to them, or anything specific, or maybe nothing at the moment? I just saw some feedback from both of you, just noted them. Okay, nothing at the moment, I guess. Yeah, all right. No, that's fine. So I just open it up to the audience. If anyone has any questions for Andre and Zuhair. I had one more, but I'll reserve it in case I get to that. So any questions?
Yes, I have a question about the distribution of the storage abstraction layer modules. Are they plugins that are loaded at runtime by the Rados gateway, or is it? Or do you have to, is it a separate software at the end? Is there a DAOS gateway or motor gateway? You have to fork the code each time?
Currently, it's source code which has to be built in with the Ceph, right? So, for example, this motor sal.c file, it is integrated into the build system of RGW. And you can specify in runtime, then in configuration file, which backend you want to use. Is it Rados or motor? And in case of motor, of course, it will try. You have to configure motor connection parameters there also in Ceph configuration file, and it will try to connect to motor. But they have a plan to move to dynamic loadable libraries, so that this SAL implementation could be just shared object libraries, which could be dynamically loaded in runtime. I think that's their plan at Ceph.
Yeah, that would be fine to have a kind of repository with all the existing backend modules, and so you can cherry pick the backends and have a larger community. Okay. And is this Rados gateway easy to install? I mean, does it pull the whole Rados Ceph, or is there a package just for the Rados gateway?
Yes, there is a RPM packet or Debian package only for RGW. You don't have, for example, in our Cortex deployments, we use only Radus gateway. We don't use any other binaries which are provided by Ceph. So yeah.
Yeah, so about that, it's something that Seagate compiled. Like if you like so far for Deos, this is not available yet. Once we are more ready to be used in production, then we will create like a Radus like gateway RPM that could be like installed in addition to Deos.
Great. Yeah, thanks.
And
Yeah, go ahead, please.
if I can ask a second question. So,
Please. Yeah. All yours, please.
yes. In your conclusion, in the perspectives, you talk about supporting both DAOs and motor to be able to switch depending on the storage you need. What mechanism would you consider to do this switch between Cortex and DAOs?
Okay, so we are still like working on the design of this project, but the idea is that under the S3 protocol, you can define object class, which normally defines like the replication levels and and in erasure coding levels and so on. So we would like to add to that we would like to add to that the ability for the user to decide which backend to use. So they could say that like I want this bucket to be all on Deos, or I want this bucket to be all on Motor, or I want this bucket to be hybrid, to be done on both. And the idea is to make like decide like some parameter that tells us like this much data should go in Motor and this much data to go on Deos. It's like basically we're trying to tier Deos and Motor under the same S3 layer.
Okay, thank you. That's clear.
Yeah, thanks, Thomas. Interesting question, because I'm thinking in my mind about one possibility for HSM when you have this layer that combines both Deos as well as Motor. There might be some interesting possibility in actually leveraging the HSM to do the data staging between the Deos and Motor. Maybe you have the M0 HSM at the moment. Maybe you need something similar, and then you use the policy engine to move across. Use the HSM tool to stage. Thomas, what do you think? I mean, is it? Am I thinking too much, or is it something realistic? If this exists,
it may. Yeah, EMOSS'22 is manage blocks of objects. I'm not sure it's suitable for the S3 protocol that more handles wall objects, even if you can do multi-part uploads, things like that.
Got it.
But perhaps using versioning could help. Having even if it's I don't know.
Yeah, no, that's interesting. You mentioned versioning. Yeah. Anyway, we'll fully get back to this. So thank you so much, Andre and Zuhair. It's very interesting to see this collaboration with different communities here. I hope that we can continue this going forward as well. So thanks. So with that, last but not the least, we have Shimon from Weka. So Shimon, can you hear me?
Definitely. Can you hear me?
Yes, we can hear you and see you clearly as well. So if I can hand you the, if you can share your screen, Shimon, and if you can start, and it'll be great if you can introduce yourself as well for our speakers. Go ahead, please.
Definitely. Thank you, Sai. So nice to meet you guys. My name is Shimon Ben David. I'm the CTO of Weka. And I wanted to present today to just introduce Weka in a few words if you're not familiar with it, but mostly talk about the design considerations and even the design itself of what we're able to do and why we're able to do and how we're able to do it. To some extent, I know 40 minutes is not enough to cover all of it, but at least some of it. I apologize in advance if some of the slides appear as an architecture, but you'll see that I'll try to keep it technical. The intention is to show what approach we took and the design considerations. So I'll jump in and definitely feel free to fine tune me with questions as we go along. So we wanted to solve, I would say, a big problem. And I'll start with that before even saying what we're doing and how we're doing it. We looked at modern workloads, and we understand that we wanted to take this customer-centric approach. What problems can we help customer with, and then design around it? So if we're looking at modern workloads, and I'm sure you're all familiar with it, the single workload, it could be an AI workload, an HPC workload, or a workload in any other environment, financial, life science, healthcare, and more. It's composed out of multiple steps, right? Ingesting the data, transforming it in many ways. If there's any AI, so training, validating on it, and maybe then archiving it. So there's multiple challenges here, and the challenges are, if we're looking at it from a storage perspective, from the data platform perspective, they vary, right? There's different block IOs, different IO patterns, different file sizes. How do you mobilize the data between different locations, different protocols? So there's definitely multiple channels that are challenges, that needs to be resolved. So we wanted to take a holistic approach and see how we can solve the entire problem and not just focus on one of these stages. So that's the challenge. If we look at current existing designs, what we see is that, and again, respect, a lot of designs were designed using what existed and what was available. So for example, if we look at parallel file systems, we see that a lot of them are composed out of multiple different moving parts. So metadata servers, admin servers, protocol gateways, data nodes. You see that these layers are riding on top of other layers. So for example, local file systems that could reside on different storage environments. So for example, NVMe fabric layers for metadata, or maybe other SAN appliances, or just JBODs or JBOFs in other environments. So there's multiple layers that are working together, that are providing a solution, but they still, when you look at it as a workflow, if you look at an IO path or a metadata path, then, or a management path, then you see that different stages interact with different components, and there's not a tight coupling. So that's what we wanted to do. We wanted to make sure that what we provide can actually address the entire pipeline. So this is a bit about what Weka is doing, and I'll keep it technical as to how we're doing it as well. So we're providing a data platform that actually accelerates. It definitely has value in AI workloads, but also HPC and other environments. And what we're doing is, imagine that we are software defined, we're installed on servers, and we'll get to what that means also. And you create file systems, 1,000 or more or less on the system, and then your compute servers, eventually the customer, that's the value that the customer needs, right? To look at the data. The neat thing here is that it supports multiple protocol. So we have our own client, we support GPU direct storage, we support NFS and S3 and SMB to the same data. We're going to add more protocols in the future. And because we're software defined, we can run on-prem, but also on clouds. So whether it's local servers or whether it's cloud instances. And I'll show you that software defined design in a second, and I think it will be more apparent. So that's the view of record. That's what we're doing. We help customers access the data in all forms and shapes, on-prem and on the cloud. We do more things. Maybe I'll talk about it a bit as well. But the challenge is that what we're seeing, and I'll show it in a second, is that there's no right way. There's no one protocol that helps customers. Because again, if I'm looking at this initial slide, a data pipeline can begin throwing data into a system using many IoT devices using S3. But then when you perform your analytics on it, you need something faster. Some of it could be throughput faster, throughput oriented. Some of it could be low latency. So there's no one magic bullet, no one magic protocol. S3 is very good. It's connectionless. It allows aggregation, and it allows throughput to some extent. It's not a low latency protocol, for example. So with that, what we did, and I'll describe it at a high level here, and then we'll deep dive, is we completely redesigned all of the components of the system, all of the software components, because we're installed on commodity servers or instances. We completely redesigned all of the software components so that we have that tight integration. So from the moment an IO leaves a compute to the moment it lands on an NVMe in one of our storage nodes, we have that tight integration across all of it. And so let's deep dive and see how we're doing it. So first of all, in terms of data distribution, what we're doing is there's no, by the way, as you can see here, there's no RAID groups, RAID arrays, storage controllers, other storage environments, no local file system. Everything is on commodity servers. And what we're doing is all of the namespace, every file in the namespace, you can think about it as millions of files as well, and billions of files, everything is split into 4K pieces. So I'll take a basic example. Imagine that one client is writing a 1 megabyte file, then that's split into 256 4K pieces. So all of these 4K pieces are then striped across all of the NVMEs and all of the storage nodes. So there's no, we need one block size for some files or objects and another block size for other files and objects. Everything is in 4K pieces. This decision was made because when we looked many years ago, or a few years ago, I would say, when we looked at modern environments, we did see the improvement in network environments. So if in the past you had to utilize data locality and make sure that you're limited to some number of storage nodes, then that was because mostly networks were not so efficient. 1 gig, 10 gig, you had some InfiniBand, but if you look at current modern networks, they're at 100 gig, 200 gig, and we're already seeing 400 gigs as well. So the decision to distribute everything in 4K pieces has been made because moving a 4K piece across the network is a single-digit microsecond. Writing to an NVMe of even a local NVMe is double-digit and triple-digit microseconds. So what we're doing is, if we have many NVMEs in the environment, and even a small environment would have, I'll throw some numbers, 24, 48, or hundreds or thousands of NVMEs, it now actually means that we can utilize all of the NVMEs in parallel, and we can derive massive throughput out of them concurrently. So for example, if I'm writing a 1 meg file that translates to 256 4K pieces, now I can read and write them in parallel from all of the storage nodes. Definitely, if I'm now writing millions or billions of files, again, I don't need to throw the decision on the customer of saying, what's your RAID group, what's your RAID stripe, what's your block size. We take that optimal decision, and I'll deep dive into that as well. And when we do that, when we stripe the data across all of the environments, what we do is we also protect it. We protect it as an N+2 or an N+4 in our environment. And it's you can think about it as our own internal erasure coding algorithm, because we wanted to create an environment where even the protection is high performance. So we have a lot of IP of how we protect the data in a fast and efficient way, so that there is no performance degradation as we're doing it. So the data is striped in 4K pieces across all of the environment. And we'll talk a bit more about it in a bit. So that's the data. On the metadata side, we wanted to make sure that we avoid the problem that we see in other environments where you have a metadata server or a small subset of metadata server, and that actually translates to some bottlenecks, because what we're seeing is that maybe I have a file system and it has a metadata server, could be many users and compute servers are hitting that environment, but maybe other file systems with other metadata servers are not being used at all. So now, not all of the hardware is even being used efficiently, not all of the CPU cores, not all of the computation that is available. So what we did is we actually wrote our own scaled out metadata environment in a way that now all of the servers are also running hundreds and thousands of virtual metadata servers, and each of them is handling their own respective part of the namespace. So for example, if I have 1,000 in a very small Weka environment, you have 1,000 virtual metadata servers. On larger environments, you have even more. And what we do is we distribute the responsibility of the entire namespace across all of these virtual metadata servers, so that none of them is handling a large capacity of the namespace. So for example, and I think the next slide would show it even better. Imagine that this is all of the addressable namespace of the Weka system, and that could be in the terabytes or in the petabytes or in the exabytes, doesn't matter. Imagine that I have thousands of virtual metadata servers running across all of my Weka nodes. So there's no 1 or 2 or 3 that are designated for that. All of the virtual metadata servers are handling all of the namespace, which consists out of all of the file systems. So for example, if I have 1,000 virtual metadata servers and I'm writing 1,000 files, statistically, each of them would handle 1 file. So suddenly you see that because we're creating such a large number, the load is equally balanced. So whether I'm writing thousands of files or millions or billions of files, then suddenly the metadata distribution load is evened across all of the virtual metadata servers. Eventually, this translates to, translates to an equal load across all of the storage nodes. So you wouldn't see any one node that is buckling under metadata performance while others are not. Because we do that change in responsibility, because we do that each of the virtual metadata servers are handling a different part, then they're all equally balanced. By the way, because it's only a computation characteristics, and I'll explain about this some more, we can now migrate virtual metadata servers between storage nodes. So for example, if I'm running 100 virtual metadata servers on each of my storage nodes, and I see that they're all operating at 60% of their utilization, for example, if I see that on one of them, maybe 1 or 2 or 3, for some reason are at 70%, what I can say is, let's migrate one of them here and here and here. So now we constantly are able to fully utilize the entire environment for all of the metadata and the data. And we'll talk more about it. But that creates an environment where there's no bottlenecks in terms of metadata. And as I said before, as we scale out the environment and the data in 4K pieces, it means that I'm getting that massive throughput across all of the storage nodes as well. On top of that, as I mentioned before, we see modern workloads that are composed out of multiple I/O patterns with different protocols as well, but with multiple I/O patterns. And because we wrote everything in 4K pieces, suddenly it means that if you need a small file I/O, that's not a problem. So maybe you have a file system, and that file system has millions of large files. I don't know, 1 meg, 10 meg, gigabytes, doesn't matter. So maybe I have 1 million of these, but now I need another billion of small files, 4K files, 0K files, 10K files. We see a lot of this in AI environments or in life science environments, where these millions or multiple millions of small files as well, in addition to the large files. That's not a problem because all of the file system is in 4K. So whether I need megabytes or gigabytes or terabytes of data per second, we can do that. And also because of this architecture, and whether we need millions of IOPS, we can do that as well. So that's, and I'm going to dig more into that. Let me know if there's any questions. In addition, what we're doing is we wanted to create an environment where we can provide that massive performance, which we'll talk a bit more. In addition, what we're doing is we're utilizing our underlying layer to virtualize the capacity, to virtualize the namespace between the flash capacity and the object storage capacity. So imagine that you have a certain flash capacities, and I think we just saw a few systems that also utilizes different media types. What we wanted to enable is we wanted to create that high performance in terms of IOPS, latency, throughput, and metadata, but also that capacity tier. So we're able to virtualize the capacity, and I'll show what that means, and I'll give a real example. Imagine that you have a customer, an object store of 100 petabytes, and the file system, the flash capacity is maybe 3 petabytes. But the storage nodes, or sorry, the compute clients are now looking at that 100 petabytes through the POSIX file system. So Weka is fully POSIX compliant. There's no POSIX trade-offs here, right? And we'll see how we're doing that in a second. But you access all of that capacity through whether it's the flash capacity, whether it's the flash and virtualized object store capacity, through that entire POSIX interface. We didn't want to give hints or try to have the customer utilize the object store and the POSIX environment by himself. We virtualized that, and we're taking these decisions. And we implemented, the way we work with an object store is that, as you can see, there is no storage gateway. So all of the virtual metadata nodes and the data nodes themselves are pushing and pulling data from the object store. What we do is we actually push data in 64 megabyte pieces to the object store. And so if you have, I'll give a basic example, if you have a 640 megabyte file, that would translate to 10 objects that we place on the object store. So when you want to read, so you get that multi-part upload and download capability. And then when you want to read, we also don't need to read the entire 64 meg, because if I have a file, a 640 megabyte file across all of the environment, and that's in 4K pieces, and we dropped it to the object store in multiple 64 meg objects, now if I want to read part of it, I don't need to bring the entire 640. I also don't need to bring the 64. What we need is to only do a byte range read out of that object store and get it back. So we're doing that in order to accelerate and make the flash capacity and the HDD object store capacity efficient. In addition, we're able to send data to cloud environments, but I'll focus about it less because I want to focus on the technical part. So going back to this slide, what we showed is that the key design points of the system are that we wanted to provide throughput, apps, metadata, and latency on the same namespace, on the same file systems, across thousands of cores. So it's a fully scaled out environment. How did we do that? So every compute node runs some number of buckets. These are our virtual metadata nodes, and I mentioned that. So that aggregates to hundreds or thousands of virtual metadata nodes across the entire system. And that translates to, I'll just give another example. Imagine that we have a small environment, 10 servers. Each of it is running maybe 20 CPU cores that are allocated for Weka, but out of them, 10 are running our virtual metadata servers. So, and each of them is running, again, I'll give a small number, 10 virtual metadata servers. So now we have 1,000 virtual metadata servers, and that's a very small environment. Usually the environments that you'll see are in the petabytes. So running tens of thousands or hundreds of thousands of virtual metadata servers. The ability to do that, by the way, the challenge in scaling out metadata is the east to west chatter between the metadata servers, right? Usually design chooses a single metadata server per unit of file system or a few file systems, simply in order to consolidate all of the coherency and all of the resiliency in case one of them fails. What we did is we actually eliminated all of the east-west chatter between the virtual metadata servers. So for example, if now I have a virtual metadata server that is responsible for this part of the namespace, and maybe this part of the namespace, and that part of the namespace, it doesn't need, it's the sole owner of that part of the namespace, and it doesn't need to communicate with other virtual metadata servers. So whether you have thousands of cores working with that part of the namespace, or a single client working with multiple parts of the namespace, there's always a deterministic one virtual metadata servers that handles this request. So hundreds or millions or billions of files are accommodated by all of them, and that's how we distribute the metadata load. And even if you look on a single file, every 8 megabytes are handled by a different virtual metadata server. So if you look at HPC challenges such as end-to-one checkpointing, where you have thousands of cores dumping data into a single file or recovering from that single file, there's no one metadata server that will handle that, because even a single file is being handled by these multiple virtual metadata servers. I would say one last thing about it, the ability to eliminate the east-to-west chatter and still keep resiliency, because what happens if a server failed and it had hundreds of virtual metadata servers, is derived by our capability to use our own block layout for journaling of the metadata operations. So a metadata server doesn't need to communicate with others because it's constantly journaling its activity on our block layer and our block layout. And in case a metadata server fails, another will pick up its place, and it will just go to the known location of that journal and continue rolling forward. So there's no need for them to chatter as they do their ongoing operations. So as I mentioned, each bucket is responsible for one part of the namespace. And then if you have hundreds or thousands or more of these, then we distribute the responsibility. Mentioned the fact that we write everything in 4K pieces. And so, as I mentioned, that eliminates the hotspots, and think about the ease of designing such a system from the customer point of view. The customer doesn't need to say, hey, I need a throughput-oriented file system. I need an IOPS-oriented file system. I just work with the system. The system itself is optimized for both. And also, I'll show some performance numbers in a bit. But eventually, this is one of the main things, kind of like that provides the metadata IOPS throughput latency, performance, and as well as low latency. And that really enables modern workloads, because modern workloads are not all about throughput or one protocol. Because we are handling and managing the SSDs, the NVMEs, and I'll show a block diagram in a bit, directly, there is no underlying file system that we're using. We're able to actually manage them at the queue level. So we're able to look at, let's say that we have an environment with hundreds or thousands of NVMEs. We're constantly monitoring the status of each of these NVMEs and the queue depth of each of these NVMEs. And we're able to take decisions according to that. So for example, if we see that out of 1,000 NVMEs, 1 or 2 or 3 have a higher queue depth, we can choose to stripe our data on others for a millisecond. And then after a millisecond, maybe after we give them a millisecond to kind of like cool down and decrease their queue depth, we're able to now say, okay, let's start using them again. because the latency we provide is in the microseconds. So giving them a millisecond to drop the queue is significant. By the way, we're also able to say, if we see that as a repetitive action on some of the NVMEs, we'll just report them as problematic, phase them out of the system, and ask the operator to replace them. But we do have that tight control because we're not using any underlying hardware that is abstracting it from us. I did mention that every 8 megabyte range of a single file is handled by a different virtual metadata server. So whether you have millions or billions of files, that means that multiple virtual metadata servers would handle them, or even if you have a large file, multiple virtual metadata servers would handle them. And the virtual metadata servers persist and journal data. And as I mentioned, buckets or virtual metadata servers can fail between the compute nodes, or we can even move them between different compute nodes if we see that there's some sort of imbalance. So whenever you look at the statistics of an environment, you'll see that all of the CPUs are being used in an equal fashion for the metadata servers. So this is the block diagram of how it looks like. So if we're looking at the layers that exist in the system, so from the application point of view, the application is working with the kernel, right? I'm doing an IO to the kernel, to the VFS kernel module, right? And we added a very thin kernel module. Basically, the only thing that it does is it throws the data to our front-end client access in user space. So we didn't want to create a client node on in the kernel for many reasons. You'll see that we actually bypass the kernel for many operations. What we did is we didn't want to use Fuse or anything like that, because Fuse is low performance than what we want to provide our customers, and it's also not POSIX compliant. So we wanted to make sure that we provide a coherent scale-out POSIX environment. So we do have that kernel module that basically the only thing that it does is it's throwing the data to our client access. The client access is not part of the cluster. It's actually aware of the cluster, but it doesn't provide any service to the cluster. Clients can appear and disappear in the system, and they're transient. It doesn't have any effect on the system. But because they are aware of the system, the clients are actually aware of the configuration of the system, whether we have 10 servers, 100 servers, or 1,000 servers, or more or less. And they know which of the metadata servers is responsible for what parts of the namespace, whether they're accessing one file or multiple files. They're aware of that. So they will take the decision of, let's say that we wrote a 4K piece here. The client would know to which server, to which virtual metadata node to go to in order to service that IO. So that's the client side. By the way, as you can see, we divided the world here into user space, kernel space, and hardware. And we're always bypassing the kernel as much as we can. And you'll see that when the client communicates, even with a single client, communicate with all of the storage nodes, we actually use DPDK to bypass the kernel. And actually we wrote our own, we're using the DPDK PMD, and we wrote our own L6 network protocol that actually we communicate directly with the NIC, and the NIC communicate using our protocol with all of the communication, whether it's the client communication, whether it's the storage node communication. The thing is, we didn't want to utilize an existing protocol as well. So by the way, bypassing the kernel is very important for us because the latencies that we provide are in the microseconds, and we didn't want to throw data to the kernel that would throw it to the NIC, because what if the kernel is doing something else that we don't control, paging a log file or handling another IO that is not as important as this IO. So we could wait a millisecond for the kernel to do that, and because we want to provide 100, 150 microsecond, that's eternity for us. So bypassing the kernel is essential, and it means, by the way, that the customer can run any kernel that they want. We don't limit the customer configuration for that. We don't force them to use like our own highly optimized kernel, because we just bypass it. And we also took the decision to write our own network protocol, which is a very heavy lift, but it really pays off, because using DPDK does give us some DMA capabilities between the client and the storage nodes. And it also means that we're not using off-the-shelf protocol like TCP/IP, which is very good for multi-connectivity. It's less efficient for being very low latency. There's all of the TTL and the backoff window, and we wanted to control that part as well. So we actually wrote our own protocol, which appears as an IP, as a UDP over IP. That's my attempt of writing a UDP over IP, and above it, it's our own L6 protocol. So we manage all of this layer and just send it over UDP over IP. So we can manage the how aggressive it is. So the client that is communicating with multiple virtual metadata servers using our own protocol, now the virtual metadata servers, by the way, the client, in order, and that's another key design point, in order to be able to truly scale out an environment, we need to make sure that there are no resources that are depleted as the environment scales out. So for example, what we don't do, we don't use any tables in memory that would manage the client knowledge of the system, that would say which metadata server handles what part of the namespace. We don't do that. So everything in the system is calculation based. So I'm a client, I need to go to access a certain block range within a certain file. I now do a simple calculation with that block range and path, and I know in a deterministic way which of my virtual metadata servers would handle that and which node handles that virtual metadata server. So I don't need to expand a memory table or to spend memory lookup cycles in order to get that. So it's a very cheap calculation to know where to go. And then, as I mentioned, we go over our protocol to these environments, and I could go to all, and usually you'll see that the client communicates with all of the storage nodes in parallel for that virtual metadata. The virtual metadata servers would either reply back with which NVMEs hold the data. As I mentioned, let's say that I'm looking for 4K, that would reside on one NVMe. Let's say that I'm looking for one file that is 40K or 1 meg. I'll now get the knowledge of which 256 NVMEs and where in them the data resides. So everything is scaled out and distributed. And now I'll go to our other component, which we call it the SSD agent, which is hold the knowledge that there's an SSD agent on each of the storage nodes, again, one or more, that is managing the block access. You can think about it as CPU cycles per block throughput and IOPS, because eventually there's a calculation of how many CPU cycles can derive how many IOPS per NVMe. So maybe we have 10 CPUs running that, or maybe we have 2 or 1 or 3. It all depends on the number of NVMEs that a certain server has. And there's a ratio that we maintain. But eventually that SSD agent, when a client, and maybe I'll erase this and start again. When a client is asking for data and it knows, hey, you need to give me the data, that SSD agent would actually know where the data is, because we handle the SSDs also in their block layer. As I mentioned, there's no other underlying file system. And then it would provide the data to the client. And that happens with tens or hundreds or thousands of servers concurrently. So that's the benefit of being fully scaled out. As you can see here, we also bypass the kernel when communicating with the NVMEs. So there's no kernel, there's no NVMe driver that the kernel is using for the Weka environment, because the kernel NVMe driver is generic. It handles multiple IO patterns for multiple things, right? We wanted to write our own optimized access to the NVMEs. So we have our own user space NVMe driver that we wrote using SPDK. And that actually provides massive performance because we know how to prepare the data, to drop it to the SSD in a performant mode that would benefit Weka. So, and there's many ways to talk about it. I'll give a few examples, by the way. Imagine that we're now writing 4K, so as all of the data is in 4Ks. So maybe I'm writing 256 4Ks, dropping them to the NVMEs. We wouldn't drop them in 4Ks because we wanted to make sure that the NVMEs are getting into their throughput mode to get as much performance as possible for them. So imagine that we're aggregating the 4Ks. Each of this is a 4K, for example, 4K, 4K. So we're aggregating all of the 4Ks into one large block, and we're dropping that as a larger block to the NVMe. So the NVMEs are now kicking into their throughput node. So even though the compute client is writing in 4Ks, we're aggregating them and dropping them to the NVMEs in larger blocks. But when you need them, you can still read a 4K. So there's no read amplification. So you don't need to read a 1 meg or 32K even only to provide a 4K. You just need to read the 4K. So these are some of the design considerations. Scale out is definitely the main one. And in order to scale out, it's scaling out the data and the metadata. I think if I'll show kind of like a naive IO path and the difference, if you're looking at NFS appliances, this is usually an IO path. Again, it's very basic. It's eliminating a lot of layers, but imagine that you always have a one-to-one connection with an NFS head. Could be that you have a scaled out NFS environment, but your NFS mount is a one-to-one. Maybe there's some communication between the NFS nodes, but you're very limited on what the NFS as a protocol can do, but also what NFS heads can provide. On parallel file system, you have that notion of metadata server and the data nodes. And again, in many cases, we're seeing that you have a metadata server per file system, even and an admin server per file system. I'll stop it here. But basically, in many cases, you're bottlenecking your metadata server while not all of the other environment is fully utilized. And you're very much throughput oriented. Again, these environments were designed when HDDs were created, and that was the smart thing to do back then. With the Weka, this is, again, conceptually thinking about it, how an environment, how an IO looks like. So everything, all of the IOs, even a single file, and I'll stop here, goes to multiple virtual metadata servers, and from them to multiple SSD agents, or directly even, depends on how we're doing the reads and the writes. And because everything is fully scaled out, everything is fully utilized. So imagine a day one environment where you have 10 servers and you fully used the CPU resources for data, metadata, the CPUs and NVMEs. You can always scale out more. You can always add more servers, 10 or 1 or 2. Doesn't matter. You can always add more nodes, and we'll just rebalance the metadata responsibility across them. And we'll also rebalance the data striping across them. So now, just by adding more servers without any downtime, because we control the entire IO path, we can do all of these things without any downtime and not force the customer to unmount the data or anything like that. Eventually, where does this translate to? It provides many things, but if we're talking about performance, and again, this is not a marketing slide, so it doesn't matter what these environments are. Sufficient to say that when we just look at throughput and IOPS per 1 petabyte, and we compare it to other industry numbers that are published by the vendors, again, doesn't matter who they are, you can see that we're capable of that scale out massive design can provide millions of IOPS and terabytes per second, all on the same file system, not even splitting different file systems. And I'll show another thing. For example, when we utilize GPU direct storage, showing the same thing, massive throughput and massive IOPS on the same environment. And I think I'll finish with one last thing. because this is a scale-out environment, because it's able, it's fully software defined, because we implemented all of the kernel bypass environment, we're definitely able to scale out to cloud environments. So one of the key design points is that modern environments, and if I'm kind of like looking at the bigger topics of how does this enable modern environments are cloud native. They can run on multiple containerized environment on-prem, they can run on the cloud, they can burst between them, they should be even cloud agnostic to some extent, aside from the orchestration part, right? So the ability to say, hey, we implemented all of the layers, all of the kernel bypass layers, and we don't require any specific hardware characteristics, actually means that we can run on the cloud as well as on-prem. And because we have the capabilities of sending data to different locations, which we didn't cover because it's less this topic here, we actually don't need, we actually are able to burst the data and burst the compute to the cloud. I think I'll stop here. I think I see some questions on the chat.
Thank you, Shimon. I think it's general comments from the audience, but very crisp, very nice presentation. I think it was very clear for me at least. So thank you so much. I have a bunch of questions for me. I was very curious about a few things, but let me check with the audience if they have anything. Perhaps they might be still thinking about it. Any questions for Shimon? Yeah, so just a few things, right? So it looks like the way you have layered the stack, even you have the on-prem object storage is your fundamental backend store, so to speak. So is that correct for the data?
We see on-prem object storage as an option component. So we do have customers, but it's important, I'll elaborate on that. We do have customers running multiple petabytes of a flash environment, even more than 100 petabytes on an all-flash environment. But we also see customers that for better TCO do prefer, and I didn't mention that, but we were able to get massive performance from the object stores as well, because of a lot of the things that we're doing. And I'll be glad to elaborate when we have more time. But we do see that as a critical part of the system because that exists in many layers. And when you want to create that hybrid cloud notion, you definitely do want to use object storage. The way we use object storage is mostly for their throughput, because we can derive massive throughput out of them, and also because of their improved TCO. Because it's funny, but somebody once told me the fact that you're able to use object storage, and which essentially are very hard drive based, is future-proofing them, because you can see that the cost of HDDs is still definitely better than NVMe. So utilizing that, that together is very massive.
Got it. Yeah. Thank you. And also the if I may, Shimon. So you mentioned you use protocols like simple UDP between the client and server and things like that, which is very good, because we'll obviously bypass all the problems and bottlenecks of TCP, TCP/IP and things like that. But what about like data loss? Because UDP obviously is very lightweight. Maybe you don't foresee data losses in a closed environment.
We do. It's a great question. I'll say it clearly. In our design, even though we're software defined, or especially because we're software defined, we assume that hardware is going to fail constantly. Sometimes it will just fail. Sometimes it will, for example, in network, you'll get bit error bears, right? In the network, sometimes there will be disconnections. Definitely. So the environment, as I mentioned, even though we're using UDP, that's the transport mechanism, or UDP over IP, we do have our layer 6. So when you look at that, our layer 6 protocol on top of it implements what TCP would have managed, right? So for example, TCP would have managed the drop of connections and the retries, but TCP is very, very focused on connectivity, but not focused on low latency and high performance. So we implement all of these layers. So you literally have environments where packets are dropped, by the way, we will retransmit, we will take care of that. We'll make sure that the data arrives as it should, and we will also alert. So it wouldn't just be hidden. I'll give you an example. One of the things that we're doing is for every 4K packet, we're checksumming the 4K packet. So let's say that you wrote a file, maybe a year later or a second later, you read it. We will know if when you read it, what you got is identical to what you wrote. Because it could be that there's a bit flip on the network or a bit flip on the NVMe. So if we detect that, we'll actually fix it, because we'll do a degraded read and make sure that you get the correct data. But we'll also say, hey, there was a bit flip or something happened here. And we saw already in some supercomputing centers where that happens, and suddenly they use incorrect cables, for example, because at scale, you see more problems. One of the things is that we're also supporting InfiniBand. So we mentioned Ethernet-based protocol, but we do support InfiniBand, and we do have massive installations. Actually, a lot of the largest installations are on InfiniBand network.
Got it. Okay. Yeah, I think that clarifies. Yeah, thank you so much. Yeah, I'll open it up if someone else has any questions.
Yeah. So Shimon, you said that you use 4K units for any objects, right? So for 1 megabyte object, you have 256 units to be sent, right? And for 10 megabyte object, it will be 2,000 something. So how do you handle this? Doesn't it generate too many packets to be sent?
Actually, when you look at the network, it doesn't. I'll explain why. When you look at the network, modern network MTUs, the transmission units, are above 4K. So by default, you have 15K. But if you're using jumbo frames and you're using more than 4K, so when you look at it, every 4K is one transmission unit. So even if we wouldn't have done that, let's say that you are now writing a 1 meg object to one server, you're now sending 256 packets to that server specifically. Anyway, even if, let's say that your MTU is 4K, if your MTU is not 4K and it's 1500, you're even sending more. So the fact that we split it to 4K and we're able to distribute it to multiple servers means that suddenly now I'm not bottlenecking that. I'm not end-to-oneing that one server with 256 packets. I'm sending 256 packets across multiple servers. So actually, it means that we're distributing the load that you would have had anyway in a scale-out environment. Make sense?
I didn't get that bit that I would have it anyway. Why?
I'll give an example. Let's say that you have one client and you're not doing that 4K distribution. You're writing 1 meg pieces or 10 meg pieces. So now that your client is sending 10 meg to one storage node, right? In this example. On the underlying network layer, the data is not sent as a one packet of 10 megabytes. The data is anyway split into 1500s or 4Ks or 9Ks, because that's the network layer. So you will anyway send that number of packets in this. Does that make sense? In the environment where all of these packets needs to go on to one server, because that's your block size on that one server, you now are throwing all of them to that one server. With us, you're throwing it in 4K pieces to all of the servers concurrently.
I don't agree that data is split anyway. For example, we do in Motor, we do zero copy in this protocol. How is it called? Which does zero copy. What is it?
But do you mean RDMA?
Yes,
Yeah.
RDMA.
But again,
And
RDMA
it doesn't split the data, right? For example, if you want to send 1 megabyte chunk, you do 0 copy and you will send it in 1 megabyte chunk.
No, you will not. You will also split it because RDMA writes over InfiniBand. InfiniBand is your transport layer, and InfiniBand or Rocky, if you're doing it on Ethernet, has an MTU. So eventually, you will also split it, whether you do it or the protocol underneath you does it. It will also be split into 4K. Actually, the InfiniBand maximum transfer unit is 4K. So you're doing RDMA. RDMA is not related to how you send it on the wire. It's more related to the fact that you will send it directly to a memory buffer that is mapped on the other side. But the network transport is actually the same. I hope you're doing it in large packets and then you're decreasing the number of packets as well. But the fact is that still, if you're doing a 1 meg, InfiniBand under the hood would split it for you to 256, and you will send 256 packets. And again, the difference is that in your case, you would send it all to one server. We would send it to multiple servers.
Yeah.
Okay, thank you.
Yeah, I see what you mean. Yeah, thank you. Yeah, thanks, Simon. So it's great. I think we can keep talking about this forever, but we don't have so much time, unfortunately. So I think we just have last 10 minutes. So I just had a couple of questions prepared for the whole panel here. So thank you so much for the talk, Simon. So I'll definitely look for some other opportunity to re-engage and learn more about Veka.
I can talk for days about it.
That's very good for us, right? That's awesome. So then just open the question for the panel. Now, unfortunately, Thomas had to leave. But we've got Philippe and Zuhair and Andre and yourself. So just one quick question for all of you. Like we have a lot of people from the budding students who are learning about in the academic world, trying to learn about storage and thinking about big problems to solve. And some of them are also contributing to open source, right? So for them, can I just just go over all of you and just can you guide them about some of the big problems that you see in storage and storage software or storage infrastructure that they really need to, that's very interesting for them to probably solve. So I know it's all of a sudden I'm throwing an abrupt question, but just thinking about our community, right? So yeah, what are your thoughts on those big problem areas in storage? So Philippe, can I give you the spotlight maybe?
Yeah. I think one of the challenge we have today is to imagine what will be the world without POSIX, without the usual file systems. And I'm really focusing on the largest HPC sites or AI sites, and when you are tackling with very big size problems, but we all think that the POSIX standard with the strong coherency model will not be the right solution anymore. So how can we replace that by what? And from the talk today, I think we had proposals, for instance, to implement sophisticated HSM features where I can control the layers, the volumes, and decide where my data will go. And I was wondering, how can we expose that kind of features to users, and what will be the interface for users?
Got it. Thank you. So basically, it's about now looking at how the problems of POSIX and also how you can leverage hierarchical storage and how you can leverage. So that you think are good problems to look into. Okay. Thank you. Yeah, if anyone else wants to answer that, Zuhair and Andre, what are your thoughts? Or Shimon, feel free to jump in.
I always have opinion. I'll pitch in. I think if I was to start something today, I would look at, again, we're talking about storage, which is great. We're a storage person. That's my passion as well. We should look at it as in a holistic view. Not only how do I create a cool science project, how do I provide value for the challenges that customers are seeing now in a holistic view. Some of it is storage, some of it is different. Some of it is as I think Philippe mentioned, POSIX, yes or no. Some of it is multiple things. I would definitely look at AI environments. There's a lot of challenge there. Everything is going AI. We can talk about AI for hours also. And the fun thing about AI is that it's so complicated that not everything, there's no like, hey, just throw it on the GPUs or do it with PyTorch or Keras or this or that. There's like different considerations there. Also be cloud native, because everything today, even if it's not going on the cloud, it has the cloud native concept. So how do I challenge that? How do I solve for that as well?
Got it. Yeah, so basically just to follow up on that, right? For AI, I mean, what do you think are like the big problems? Because obviously you might potentially have a very small IO and you have read intensive workflows, and you have to probably stage data in higher tiers, and AI can be memory intensive. So from storage and IO perspective, and considering AI applications, right? What do you think are like big problem areas at the moment? Philippe or Shimon or Zuhair, Andre, feel free to like provide some thoughts. There's so much of AI going on, right? So it might be good to know how storage plays into that.
Indeed, the AI, one of the big problem is the data set management, data set in terms of training data, having traceability, knowing what we did with the data, in which order we trained this model, reading those files, and it's really traceability and data organization again. You cannot afford to manage millions of files just like that, putting everything in one single directory. And yeah, that's again the scalability, I think, that need probably more new way of handling data.
I'll pitch it as well. I think scalability is hugely problematic. It's important, as mentioned. I think the fact that when you look at a lot of the AI ML workloads are using some accelerators, GPUs or TPUs or IPUs, or there's a lot of these interesting companies that are doing very dedicated AI accelerators. It's eventually you want to make sure that the accelerator is constantly fed with data, that it's not idle. The investment of accelerators is so huge. And I'd even say on the human side of it, if I have a data scientist, and that data scientist, which are very hard to acquire, it's a very specific expertise. If that data scientist is working in an environment where nothing moves, they get frustrated. And we actually, in a survey that we did, we see that a lot of the challenge is retaining the human interest. So we want to make sure that your design actually is optimized for optimized result, but also to make sure that you don't lose the personnel that is actually going to derive value from that design. So that's another interesting aspect. I do agree that MLOps environments are very important. All of the democratizing AI and making it explainable so that you can constantly repeat. I think there's another challenge in AI in terms of acquiring data, and definitely with mobilizing the data between different locations, because with AI, if we all look at the edge to edge aggregation to core notion, with AI, it's even more compounded, more important, because you have massive IoT devices. This could be a car, a drone, hundreds of these, thousands of these or more, and they're aggregating data. And sometimes the location where you want to compute on that data to derive value from it, because that's the important part, right? Your workload time to value is not even in the same continent, right? And sometimes there's the technical challenge of how do I move the data around? Sometimes there's the challenge of am I even allowed to move the data? Maybe I need to do something. Maybe I need to remove PI from the data. So there's a lot of challenges.
Yeah, it's very interesting that you mentioned productivity of big data scientists who are very expensive. That's looking at the problem interestingly from an economic angle, right? Why storage needs to be good, not just from a technical standpoint, right? It's very interesting. Yeah, yeah.
One aspect is also important.
Yeah. Yeah, thank you so much. Zuhair and Andre, or any of you, any final words, anything you want to add? We are just on the hour. I need to, we need to stop in the next minute. Anything else?
No, thank you. It was interesting.
Yeah, and please mind you that this recording will be shared. So even if you don't have a big audience because of time zone constraints and everything, and these days people know that when recording is available, they tend to wait for it. So yeah, so thank you so much, everyone. So please, the proceedings should be out already. So you can check that. I just put a link. And yeah, let's look for other opportunities to engage. And yeah, it's very exciting. So I wish we could talk more, but we got to leave now. All right. Take care. Have a nice weekend. Yeah. All right.
Thank you. Have a good one.
See you, everyone. Yeah. Bye.
Bye-bye.